The Death Star galaxy, the galaxy being killed by the universe itself. Across the universe, some galaxies are not just aging, they are dying. Stripped of the gas that fuels star formation, their stars fade and their energy dwindles, all while the vast cosmic environment exerts forces beyond their control. One galaxy stands out, a massive system slowly being extinguished by the universe. The Death Star galaxy, across different wavelengths. The first view of the Death Star galaxy came in optical light, captured by one of the world's most precise space telescopes. In this light, the galaxy appeared faint but structured. Its spiral shape stretched across the sky, the arms thin and fragmented. Star clusters, normally bright and blue in active galaxies, were sparse and scattered, a subtle halo of older yellow and red stars dominating the disk. The spiral arms seemed broken in places, almost ghostly against the dark canvas of space. The central bulge glowed dimly, lacking the intense light typical of a galaxy actively forming stars. Fine details emerged in the optical spectrum. Tiny gaps where gas clouds should have been, dim streaks suggesting regions where stellar birth had already ceased. Switching to radio wavelengths revealed a completely different picture. The structures seen in optical light were overlaid with invisible streams of neutral hydrogen. Instead of filling the spiral arms, the hydrogen gas appeared scattered and irregular, flowing along paths that hinted at external forces shaping its motion. Some areas of the disk showed dense clumps of gas, while others were nearly empty. High-velocity flows carried gas away from the center, patterns impossible to detect in optical light alone. Radio observations made the galaxy's skeletal structure visible, revealing how the raw material for star formation was thinning and disappearing. The galaxy's disk looked fragmented, its life source being siphoned away piece by piece, leaving only a sparse framework where stars could no longer form freely. X-ray observations added another contrast. High-energy imaging captured emissions from the galaxy's core, highlighting activity invisible in optical and radio light. Streams of energetic particles radiated outward in uneven patterns, showing pockets of activity that did not correspond to the usual processes of black hole feeding or supernova explosions. The central region glowed faintly but irregularly, with trails of energy threading through parts of the galaxy that appeared dead in optical light. These X-ray signatures painted a picture of a galaxy under stress, subtly but persistently altered by forces beyond its own structure. The combination of these three perspectives transformed the galaxy from a faint optical smudge into a dynamic, multi-layered object. Optical light revealed the visible stars and broken arms. Radio wavelengths traced the dwindling fuel for future stars. X-ray emissions exposed hidden high-energy activity in the core. Together, the three views created a cinematic portrait of a galaxy caught in the act of dying, showing where life still lingered and where the universe had already begun to strip it away. Every telescope offered a different window into the galaxy's state. In optical light, the Death Star galaxy seemed fragile, almost ethereal, its spiral arms like fading brushstrokes. Radio observations exposed the invisible veins of hydrogen gas, twisted and sparse, drifting in unusual paths across the disk. X-ray imagery revealed the quiet struggle in the core, streams of energy flowing through empty space, hinting at forces shaping the galaxy's fate. The three wavelengths combined revealed a story no single view could tell. A galaxy alive but slowly losing the essential components for survival, its spiral structure dimming, its energy patterns irregular, and its fuel vanishing. Optical imaging allowed astronomers to map the remaining stars and identify regions of halted star formation. Radio mapping showed the movement and depletion of hydrogen gas, tracing the slow starvation of the galaxy. X-ray images highlighted energetic processes in the center, revealing stress and disruption invisible to other instruments. Together, these views made it possible to follow the galaxy's decline in detail, revealing how different layers of its structure responded to the forces affecting it. The Death Star galaxy looked different in each wavelength, and those differences were striking. The spiral arms appeared fragile and dim in optical light, empty pockets starkly visible against the remaining stars. In radio waves, the galaxy's gas was scattered, moving along paths that suggested it was being stripped away or disrupted. In X-ray light, energy flowed irregularly through the core, highlighting processes hidden from other instruments. The combination of these observations allowed astronomers to see the galaxy in a new way, revealing both what remained and what had already vanished, and showing the death of a galaxy not in explosions or collisions, but in absence, depletion, and subtle energetic stress. Discovery and first observations of the Death Star galaxy. The first observations came from optical surveys. Astronomers had catalogued millions of galaxies, and this one seemed ordinary at first. Its shape resembled a spiral, with a faint disk and hints of stars spread across it. Nothing immediately suggested that it would become one of the most unusual galaxies ever studied. Yet when researchers looked closer, using different instruments to study its structure and light, the galaxy revealed its secrets. Its star formation was unusually low. In a typical galaxy of this size, clouds of gas collapse to form new stars, brightening the spiral arms with young blue stars. But in this galaxy, the gas clouds were thin, scattered, almost empty. Star formation had slowed to almost nothing. That was the first clue. The next breakthrough came from radio observations, conducted using the Atacama Large Millimeter Submillimeter Array, or ALMA, in Chile. ALMA measures cold molecular gas, the raw material for new stars. Its measurements revealed that this galaxy had very little cold gas left. Most galaxies of similar size and type are brimming with this gas. They are full of the fuel that drives star birth. The Death Star galaxy had almost none. ALMA detected only traces of molecular hydrogen, the building block of stars, and those traces were unevenly spread across the galaxy. It was clear that something had stripped the galaxy of its ability to form stars, and scientists began to sense that they were looking at a galaxy in the process of dying. Then came the high-energy observations. Space telescopes sensitive to X-rays, such as Chandra, were brought in to check the galaxy's central regions. These observations detected unusual energy flows, patterns that did not match the usual activity of black holes or supernova explosions. The galaxy's core emitted energy in a strange, uneven way. It was active, but not in the way astronomers expected. Usually, a galaxy with low star formation might show signs of violent activity from its central black hole, but that was not the case here. The energy readings suggested something different, an external influence, a force from outside the galaxy that was affecting its structure. The discovery can be traced to a team of astronomers working to understand galaxy evolution. They noticed anomalies in the data while comparing galaxies of similar type and size. These anomalies were subtle at first: lower than expected star formation, less cold gas, strange energy emissions. No single measurement was enough to draw attention, but when data from Hubble, ALMA, and other observatories were combined, a pattern emerged. The galaxy was dying not because of internal events, but because of the environment around it. The universe itself seemed to be slowly shutting it down. Excitement built slowly, first within the research team. The unusual properties sparked debates and checks. Could the instruments be wrong? Could this be a measurement error? Every possible explanation was tested. Observations were repeated. Other telescopes joined in. Data was scrutinized for months. The galaxy refused to conform to normal expectations. Each new dataset confirmed what the first hints had suggested. This galaxy was in trouble, and its problems were not caused by collisions or explosions, but by a cosmic-scale process that was stripping away its ability to form stars. The unusual nature of the galaxy caught the attention of the wider scientific community. When the findings were presented at conferences, discussions became heated. The galaxy's low star formation, irregular gas distribution, and strange energy readings challenged traditional ideas about how galaxies evolve. Most models assume that galaxies slow down star formation due to internal factors: a black hole consuming gas, or a wave of supernova explosions blowing out material. None of these applied here. This galaxy was alive but slowly suffocating, a process that could only happen because of forces outside itself. Hubble provided the high-resolution optical images that allowed astronomers to map stars and structures. ALMA measured the cold gas essential for star formation. X-ray observations from space telescopes detected energy flows that revealed the unusual dynamics of the galaxy's core. Radio telescopes in other locations confirmed the movement and distribution of gas in the galaxy's outskirts. Only by combining these observations could astronomers see the full picture, a galaxy being killed by the universe itself. Early reports circulated quietly at first, shared among researchers and observatory teams. They were cautious, aware that extraordinary claims require extraordinary evidence. But every new measurement supported the same conclusion. The galaxy's unusual features were persistent, measurable, and impossible to ignore. The more the galaxy was studied, the more its story became clear. It was dying, and the reason was written in the structure of the cosmos itself. The galaxy was slowly losing its gas, star formation had nearly stopped, and external forces were reshaping its future. This galaxy's first observations revealed a cosmic paradox. It had the structure of a normal galaxy, but the life signs of a dying star. Its spiral arms appeared faint, almost ghostly, with pockets of old stars scattered across a sparse disk. The cold gas that should have fueled bright new stars was nearly absent, and the high-energy emissions from the core defied easy explanation. Combining these facts painted a picture that was impossible to ignore. This galaxy was not simply aging, it was being killed by processes outside itself. As more telescopes focused on the galaxy, the story unfolded in layers. Optical, radio, and X-ray data merged into a portrait of a galaxy in slow-motion decline. The first signs of unusual behavior, low star formation, missing gas, abnormal energy flows, had evolved into a clear pattern. The galaxy's death was visible not in explosions or collisions, but in absence, in the depletion of the materials that make stars possible. Every new observation confirmed it, and each confirmation made the galaxy's story more gripping. By the time the discovery reached the public, astronomers were confident they were witnessing something entirely new. The galaxy had earned its nickname, the Death Star Galaxy. The name captured the imagination because it suggested a cosmic force extinguishing life, a galaxy slowly silenced by its surroundings. Images released to the public revealed faint spiral arms, scattered stars, and eerie gaps where gas should have been abundant. These visual cues helped convey the galaxy's unusual nature in ways numbers alone could not. Anatomy of the Death Star Galaxy. The Death Star Galaxy sits hundreds of millions of light-years away, a faint presence in the vast darkness between the stars. Measuring its size, astronomers discovered a galaxy of substantial breadth, its disk stretching across tens of thousands of light-years, wide enough to rival some of the larger spirals in its cosmic neighborhood. It has mass comparable to a standard spiral galaxy, heavy enough to hold billions of stars in orbit, yet strangely lifeless in places where brightness should dominate. The mass is concentrated, dense at the center, tapering off toward the edges where the spiral arms fade into near invisibility. Despite its scale, the galaxy exudes an eerie emptiness, a subtle warning that something is preventing it from sustaining the vibrant cycles of stellar birth common in other galaxies of its type. It is classified as a spiral galaxy, though one unlike any others documented. Its disk rotates in a familiar, gentle curve, yet the arms appear thin, fragmented, and stretched, giving it the appearance of a galaxy being pulled apart. In many spiral galaxies, these arms glow bright with clusters of young, hot stars. Here, the arms are ghostly. Star clusters exist, but they are sparse, isolated pockets of light surrounded by vast dark stretches of low density. The galaxy's spiral nature remains recognizable, but each turn of its arms feels fragile, almost skeletal, as if the structure is struggling to maintain cohesion against unseen forces. The central core of the Death Star galaxy dominates its heart with subtle luminosity. Unlike the blinding active cores seen in many spiral galaxies where supermassive black holes consume gas voraciously, this core emits energy in a more subdued, irregular pattern. It is massive, containing a concentration of stars and interstellar material, yet it does not radiate with the intensity that would signal a thriving galactic nucleus. Observations reveal that the stars in the core are older, dense populations that formed billions of years ago. Bright young stars are few, their absence lending the center a muted, almost hollow glow. Surrounding the core, faint streaks of dust and residual gas trace complex paths, remnants of what might have once fueled a more active heart. The core is a focal point, a gravitational anchor, yet it lacks the fiery vigor typical of star-forming galaxies. Star clusters across the galaxy tell another story. Small groupings of stars pepper the disk in irregular patterns. Some clusters shine with the soft blue-white light of young stars, but these are few. Most clusters are older, yellow to red in color, evidence of stars nearing the end of their lifetimes. The distribution is unusual. Gaps span wide areas of the spiral arms. Regions where gas that normally gives birth to stars is nearly absent. In standard spiral galaxies, clusters form along dense lanes of molecular gas, creating a continuous, glittering spiral. In the Death Star galaxy, clusters appear scattered, like remnants of a once vibrant system, highlighting areas where stellar formation has already ceased. The arms are dotted with these pockets of light, but vast dark stretches separate them, reinforcing the sense of a galaxy in decline. Gas and dust are critical components that reveal the galaxy's true condition. Optical images capture the faint glow of older stars and the subtle shadows of dust lanes threading the disk. These dust lanes trace the spiral structure, though they are thinner, broken, and inconsistent compared to healthy galaxies. They mark areas where gas and dust remain, material that might yet form stars, though most of it lies in sparse patches. Observations in radio wavelengths reveal more about the galaxy's fuel for star formation. Neutral hydrogen gas, essential for collapsing into molecular clouds that birth new stars, is scattered and irregular. Dense regions are confined to the outer disk or along fragmented filaments, while much of the galaxy's inner arms appear empty, stripped of the gas necessary to sustain stellar activity. ALMA observations in millimeter wavelengths detect molecular clouds, yet they are few, isolated, and weak, drifting across the disk in patterns that suggest disruption. Dust distribution provides additional insight into the galaxy's fragility. Infrared imaging detects faint, residual dust heated by the few young stars that remain. This dust is patchy, concentrated in tiny pockets, rather than forming continuous lanes along the spiral arms. The distribution of gas and dust together reveals a galaxy in transition, one that retains structural identity but lacks the materials needed for growth. The combined absence of gas and patchy dust clouds explains why star clusters are isolated, and why the spiral arms appear skeletal. The galaxy's architecture remains intact, yet the lifeblood of creation, gas and dust, has largely disappeared from regions where it should be abundant. The Death Star galaxy's rotation adds complexity to its anatomy. Radio observations reveal the movement of hydrogen gas and the orbital paths of stars across the disk. Rotation curves show a typical spiral pattern near the core, where mass concentration maintains strong gravitational control. In the outer disk, however, the movement of residual gas appears irregular, drifting along paths misaligned with the spiral arms. These anomalies suggest that forces beyond the galaxy, perhaps intergalactic flows or tidal interactions, are influencing the movement of material. The galaxy's rotation preserves the overall spiral shape, but does not fully control the distribution of its gas, leaving gaps and filaments that emphasize its unusual nature. Star populations vary widely within the galaxy. The core is dominated by old stars, densely packed, producing most of the light visible in optical wavelengths. Spiral arms host a mix of older stars and small clusters of young stars, though the younger population is minimal. The lack of large numbers of bright young stars explains why the arms appear faint and stretched. Regions that would normally be dotted with vibrant blue clusters are empty, creating visual corridors of darkness between luminous pockets. Observing the galaxy in optical wavelengths, these differences stand out, providing the first clues that the galaxy is undergoing a unique decline. One not caused by collisions or explosions, but by subtle depletion of its essential materials. Radio imaging highlights the skeleton of the galaxy, tracing hydrogen clouds that linger in the disk and outskirts. Gas moves along filaments that suggest external stripping or displacement. The pattern is not chaotic, but neither is it orderly. The distribution is fragmented, forming isolated patches instead of the dense, continuous clouds that characterize active spiral galaxies. These patterns reveal a galaxy in the act of losing its raw material, the fuel required to sustain star formation. Gas that remains moves irregularly, sometimes drifting away from the spiral arms, sometimes forming wispy filaments around the galaxy. ALMA's measurements of molecular gas further emphasize this pattern, showing weak, sparse clouds scattered across the disk. High-energy X-ray observations provide a third perspective. The core emits faint, irregular streams of radiation, highlighting pockets of energetic processes. The X-ray emission is weak relative to other spiral galaxies of similar mass, but is unevenly distributed. Some radiation flows along paths connecting the core to the inner spiral arms, tracing material that is still interacting with central gravitational forces. The rest of the disk is nearly quiet, lacking the X-ray signatures of supernova explosions or black hole activity. The pattern reinforces the impression of a galaxy struggling to maintain activity, alive in structure but depleted in the mechanisms that drive growth and brightness. The combination of these wavelengths, optical, radio, and X-ray, creates a multidimensional portrait of the Death Star galaxy. Optical light maps the stars and spiral arms, showing broken, faint structures dominated by older stars. Radio waves reveal the distribution and movement of gas, exposing depletion and irregular motion. X-ray imaging shows energy flows and weak activity in the core, highlighting stress and depletion. Together, the three perspectives reveal a galaxy that retains its architecture, but suffers an invisible, gradual death. Its anatomy is clear. A dense core, sparse star clusters, fragmented gas and dust lanes, and a skeletal spiral structure stretched across the darkness. The distance of the Death Star galaxy adds perspective to its anatomy. Hundreds of millions of light-years separate it from Earth, meaning the light-reaching telescopes today left the galaxy when its decline had already been underway for millions of years. Studying its anatomy is studying a galaxy in mid-transition, frozen in a moment of decline visible across the universe. Its size, mass, and structure allow astronomers to trace the slow depletion of gas and the fading of star-forming regions, offering a unique window into the life and death of spiral galaxies under extreme conditions. The Death Star galaxy, anatomy of a dying spiral. The first striking feature is the lack of star formation. In optical wavelengths, most spiral galaxies show glowing lanes of young blue stars weaving along the spiral arms. In the Death Star galaxy, these lanes are broken, scattered, and faint. Tiny clusters of young stars appear, isolated, surrounded by vast stretches where no new stars are forming. The optical disc shows hints of faint blue light here and there, but these are exceptions, not the rule. The spiral arms themselves are interrupted by wide gaps, zones where the usual brightness of star-forming regions is absent. In radio wavelengths, the galaxy reveals its skeletal structure in a different way. Hydrogen gas, normally the fuel for star formation, is depleted and irregularly distributed. Dense clouds that should have formed stars are fragmented, scattered across the disk in sparse filaments. The outer arms show isolated pockets of neutral hydrogen, drifting along irregular paths that do not follow the smooth spiral rotation. Some gas is slowly moving away from the disk. High-velocity flows that suggest external stripping. ALMA and other radio observations detect traces of molecular gas in tiny patches, but these are not enough to sustain normal star formation. The galaxy's gas reservoir has been drained, leaving the visible disk hollow in areas where new stars would normally illuminate the spiral arms. X-ray observations reveal high-energy outflows from the central core, faint but persistent streams of radiation threading through the inner regions. Unlike other spirals where a supermassive black hole dominates with steady accretion, this galaxy shows sporadic, uneven, high-energy activity. These outflows interact with the remaining gas, preventing the assembly of molecular clouds and stripping material from regions where star formation might still occur. The X-ray streams do not dominate the galaxy's energy output, but they are enough to maintain disruption across the disk, keeping star formation low and scattering residual gas. The central core itself is massive, a dense knot of older stars, glowing faintly in yellow and red light. Optical images show a soft halo surrounding the core, with no significant concentration of young stars. The core dominates the gravitational dynamics of the galaxy, anchoring stars and residual gas, but it does not radiate with the intensity of a star-forming nucleus. Infrared observations reveal thin, fragmented dust lanes threading through the central region, the remnants of molecular clouds that once contributed to star formation. These dust lanes are sparse, concentrated around isolated pockets of gas, and do not form the continuous structures seen in active spiral galaxies. Across the disk, star clusters appear isolated and widely spaced. Optical imaging shows these clusters as small islands of light, mostly composed of older stars. Young clusters are rare, blue-white and faint, embedded within scattered molecular clouds. The spiral arms lack the continuous chains of bright clusters typical of healthy spirals. In radio wavelengths, the hydrogen gas near these clusters is minimal, often drifting away from the disk. The molecular clouds surrounding the clusters are weak, fragmentary, and misaligned with the spiral arms. The galaxy appears alive in structure, but its life processes are failing. The spiral arms themselves are stretched, broken, and faint. Optical light reveals gaps between clusters and zones of dark emptiness where no stars are forming. The arms retain their curvature but lack the density of stars and gas that give other galaxies their vibrancy. Radio observations show filaments of hydrogen weaving through these arms, irregularly aligned, sometimes drifting outward from the spiral pattern. Molecular clouds are scattered, thin, and weak, unable to form new stars. The combination of low star formation and depleted gas gives the galaxy its deathly appearance, wide, ghostly arms with faint traces of stellar activity. High-energy outflows from the central core interact with the disk. X-ray imaging shows streams of radiation extending into the inner arms, heating remaining gas and preventing it from collapsing into new stars. These outflows, though faint compared to active galactic nuclei, are enough to disrupt molecular clouds, scatter residual hydrogen, and maintain the suppression of star formation across the disk. Infrared observations reveal small patches of dust near these streams, traces of gas and dust caught in the flow, emphasizing the fragile state of the galaxy. In the outer disk, star clusters are fewer and widely separated. Optical light shows older, redder stars dominating these regions, with minimal presence of new stars. Radio measurements show isolated hydrogen clouds drifting along irregular paths, misaligned with the spiral arms. The depletion of cold gas is nearly total in many areas. Molecular clouds are weak, dispersed, and unable to sustain star formation. X-ray streams, although primarily concentrated in the central region, extend outward in faint traces, maintaining disruption even at the edges of the disk. The outer spiral arms are a patchwork of empty regions and isolated stellar islands, a visual representation of a galaxy stripped of life-giving material. Dust distribution is sparse and patchy. Infrared imaging shows thin, delicate lanes of dust threading through the disk and around residual molecular clouds. These lanes are concentrated around remaining star-forming pockets, often near the central core or scattered along the spiral arms. The majority of the disk has minimal dust, reinforcing the skeletal appearance seen in optical wavelengths. The lack of continuous dust lanes contributes to the difficulty of forming new stars, leaving the galaxy largely inert despite its spiral structure. Rotation patterns reveal the fragile balance within the galaxy. Stars in the core follow regular orbital paths, maintaining the dense central mass. In the outer disk, hydrogen clouds and residual gas move irregularly. High-velocity flows carry material away from the disk, while some filaments drift misaligned with the spiral pattern. The rotation preserves the overall spiral form, but the irregular gas motion underscores the depletion of life-giving material. External forces, likely intergalactic flows or tidal interactions, interact with the disk, maintaining the stripping of gas and suppression of star formation. The lack of star formation, depletion of cold gas and high-energy outflows combine to create a galaxy that is alive in form but dying in function. Optical, radio, and X-ray wavelengths together reveal its anatomy. Thin, fragmented spiral arms, isolated star clusters, depleted molecular clouds, faint dust lanes, and streams of high-energy radiation moving through the core and inner disk. Every wavelength contributes to the portrait of a galaxy struggling to survive, a system with structure intact, but processes failing. Optical imaging emphasizes gaps between star clusters and dark zones in the spiral arms. Radio wavelengths reveal depleted hydrogen and filamentary flows, showing where gas has been stripped or moved away. X-ray imaging captures the faint high-energy outflows, disrupting the remaining material. Infrared data traces patchy dust near surviving clouds. The combination of these views gives a multidimensional portrait of a galaxy slowly losing the elements that sustain life: new stars, gas, and molecular clouds. The Death Star galaxy's spiral arms, while intact in form, are skeletal in function. Star clusters are isolated and widely spaced. Molecular clouds are sparse, weak, and misaligned with the spiral structure. Cold gas is nearly gone in much of the disk, and high-energy streams continue to disrupt what remains. The visual effect is of a galaxy whose arms stretch across space like faint, ghostly veins, glowing faintly where pockets of life persist, but dominated by darkness, absence, and decay. High-energy outflows persist in the central core, faint streams interacting with the inner spiral arms. Gas is heated, scattered, and prevented from condensing into new stars. Dust is patchy, forming delicate lanes around residual molecular clouds. Star formation is nearly extinct, with only rare, isolated pockets where conditions still allow small clusters of young stars. Hydrogen gas continues to drift along irregular paths, moving away from the disk in a slow, persistent depletion. The central core remains the brightest region, composed of dense, older stars. Optical light shows the soft yellow glow of stars billions of years old. X-ray imaging captures faint, energetic streams moving outward, interacting with gas and dust. The combination of gravity, depleted gas, and energy flows creates a dynamic environment in which new star formation is almost entirely suppressed. The spiral arms stretch outward, skeletal in appearance, fragmented in optical light, depleted in gas and dust, and disrupted by high-energy phenomena. The outer disk contains scattered, isolated star clusters and traces of hydrogen gas. Optical images show redder, older stars dominating the region. Radio wavelengths reveal filaments of hydrogen drifting irregularly. Molecular clouds are few and weak, incapable of sustaining ongoing star formation. X-ray streams, faint but persistent, reach outward into these regions, continuing to maintain disruption. Dust lanes are thin and fragmented, emphasizing the empty spaces between surviving clusters. Every observation reinforces the galaxy's deathly characteristics. Star formation is nearly extinct, cold gas is depleted across the disk, and high-energy outflows disrupt residual material. Optical, radio, and X-ray wavelengths combine to give a multi-layered, cinematic portrait of a galaxy, alive in shape but dying in function. A system slowly stripped of the material needed to sustain its spiral arms and star clusters. Comparison with similar galaxies undergoing star formation. The universe is full of spiral galaxies that shine with life, stretching across space with arms alive in color, energy, and motion. Unlike the Death Star galaxy, these galaxies are rich in young stars, abundant in gas, and vibrant in the signals of star formation. The difference between a typical star-forming spiral and the Death Star galaxy is immediately apparent when observations in multiple wavelengths are compared. Optical light shows the first striking contrast. In a galaxy undergoing active star formation, spiral arms are densely populated with luminous blue clusters. These clusters appear in lines and arcs along the arms, glowing brightly against the backdrop of older stars. The light from these young stars dominates the optical spectrum, giving the galaxy a vibrant, almost electric appearance. Dust lanes thread through these regions, dark and opaque against the glowing clusters, tracing the raw material that feeds star formation. In comparison, the Death Star galaxy's optical light is pale and fragmented. Its arms are broken and ghostly, dotted with only a few isolated blue clusters among stretches of dim old stars. The contrast is immediate. Where a star-forming galaxy radiates new life, the Death Star galaxy glows faintly with remnants of a past age. Examining radio wavelengths amplifies the difference. In active galaxies, neutral hydrogen and molecular gas flow along the spiral arms in dense lanes. These gas clouds are the engines of star formation, collapsing under gravity to ignite new stars. Observations reveal continuous thick filaments of hydrogen in active spirals, aligned with the spiral arms, moving in ordered rotation around the core. Molecular clouds form dense knots along these filaments, often concentrated in the inner arms or near galactic bars, feeding rapid ongoing star formation. In the Death Star galaxy, hydrogen is scattered and irregular. Filaments are fragmented, thin and misaligned, drifting away from the arms. Molecular clouds are sparse and weak, unable to trigger significant star formation. The visual difference is stark. Active spirals are alive with gas. The Death Star galaxy is hollow, depleted, and faint. X-ray observations provide another layer of comparison. In star-forming galaxies, supernovae and stellar winds generate high-energy emissions across the disk. X-ray imaging captures bright knots along the spiral arms, where massive stars explode or emit powerful radiation. The central core, often hosting a supermassive black hole, may radiate steadily, adding to the energetic environment. In the Death Star galaxy, X-ray emissions are faint, irregular, and confined to the central core. Streams of high-energy radiation extend into the inner disk but are insufficient to stimulate new star formation. Unlike active galaxies, where energy complements the gas in creating new stellar nurseries, in the Death Star galaxy, high-energy outflows disrupt remaining clouds and prevent collapse. The structure of star clusters also emphasizes the contrast. Active spirals show clusters forming along dense lanes of molecular gas, creating continuous chains of blue, young stars. These clusters often host thousands to millions of stars, contributing to the galaxy's brightness and giving the arms a patterned, glittering appearance. In the Death Star galaxy, star clusters are scattered, isolated, and mostly old. Few new clusters appear, and those that do are tiny and weak, producing only faint optical signals. The spacing between clusters highlights the galaxy's decline. Active spirals display continuous birth along their arms. The Death Star galaxy only scattered remnants. Dust distribution further differentiates the two types of galaxies. In star-forming spirals, thick dark dust lanes trace the arms, absorbing and scattering light to reveal underlying young clusters and gas clouds. Infrared imaging shows heated dust glowing along these lanes, marking the presence of star-forming regions. In the Death Star galaxy, dust lanes are thin, fragmented, and concentrated in small pockets. Most of the disk lacks the dense continuous dust necessary for efficient star formation. The remaining dust exists near isolated clusters or along residual molecular clouds, emphasizing the gaps and depleted regions across the galaxy. Rotation and dynamics provide additional contrast. In active spirals, gas and stars follow smooth, ordered orbits. Rotation curves remain consistent across the disk, and gas flows maintain alignment with spiral arms, feeding continuous star formation. In the Death Star galaxy, outer disk gas and clouds move irregularly. Filaments drift away from arms, misaligned with the disk's rotation. High-velocity flows in the periphery suggest stripping phenomena likely caused by interactions with intergalactic material. While active spirals retain stable orbital patterns to support ongoing formation, the Death Star galaxy shows disruption that prevents gas from collapsing into new stars. Environmental factors also highlight the differences. Active spirals often inhabit regions rich in intergalactic material that supports gas accretion. Streams of hydrogen or minor interactions can fuel new star formation, sustaining the vibrancy of the galaxy. In the Death Star galaxy, observations suggest external stripping or high-energy outflows remove residual gas. Where active galaxies accumulate material to feed stellar nurseries, the Death Star galaxy loses what little remains, leaving spiral arms depleted and star formation nearly extinct. Comparing the stellar populations adds further depth. In active spirals, the population is mixed, but dominated by young luminous stars in the arms, forming bright blue clusters against a background of older stars in the disk and bulge. In the Death Star galaxy, older stars dominate nearly everywhere. Optical imaging reveals faint traces of blue stars only in scattered pockets. The difference is visual and structural. Active spirals glow and thrum with life, while the Death Star galaxy appears faint, skeletal, and isolated. Infrared imaging shows thermal differences. Star-forming galaxies have widespread infrared emission along spiral arms, where dust heated by young stars radiates energy. This indicates the presence of active molecular clouds and ongoing star formation. In contrast, the Death Star galaxy shows limited infrared emission. Dust is patchy and localized, and the heat signature of star formation is weak. The arms, though present, lack the continuous thermal glow seen in active spirals. High-energy outflows further distinguish the two. In active galaxies, supernovae, stellar winds, and core activity contribute to energy distribution without disrupting the supply of cold gas. These processes coexist with star formation. In the Death Star galaxy, central outflows are irregular and disruptive. X-ray streams interact with remaining gas, stripping or heating it, suppressing new star formation. Where active galaxies use energy to sustain life, the Death Star galaxy uses energy to prevent it. Even at a larger scale, the differences are striking. Spiral arms in active galaxies are dense, structured, and continuous. Star formation occurs along entire segments of the disk. Gas filaments flow predictably, feeding molecular clouds. Dust is thick, abundant, and distributed to optimize star formation. In the Death Star galaxy, spiral arms are broken, gas is fragmented, molecular clouds are sparse, and dust is patchy. The high-energy core interacts with residual material, maintaining depletion rather than supporting growth. The comparison emphasizes the Death Star galaxy's unique deathly status. It retains shape, but not function. Galaxies of similar mass and size often display robust star formation. Optical images show glowing spiral arms full of young stars. Radio maps reveal dense molecular clouds along the arms. X-ray and infrared data indicate active cores and dust heating, sustaining formation cycles. In the Death Star galaxy, optical arms are dim and broken, radiohydrogen is sparse, molecular clouds are weak, dust is patchy, and X-ray outflows disrupt residual material. These differences highlight the galaxy's abnormal evolution compared to its peers. Star clusters in active galaxies form in chains along gas-rich spiral arms. Bright clusters, blue and dense, illuminate their surroundings. In the Death Star galaxy, clusters are isolated, small, faint, and mostly old. The distribution is irregular, emphasizing depletion and disruption. Comparing the cluster patterns shows the absence of normal stellar birth in the Death Star galaxy, a key factor distinguishing it from active spirals. Gas density contrasts reinforce this picture. In star-forming galaxies, gas is dense and aligned with spiral structure. Filaments provide continuous material for star formation. In the Death Star galaxy, gas is thin, irregular, and often drifting away. ALMA imaging confirms fragmented molecular clouds and high-velocity flows, while neutral hydrogen maps show depletion across the inner and outer disk. Where typical spirals build stars along dense gas lanes, the Death Star galaxy loses its potential for growth. Even core activity differs fundamentally. In active spirals, core radiation complements star formation. Gas is funneled inward, supporting both central and peripheral formation processes. In the Death Star galaxy, the core's X-ray emission disrupts remaining gas. High-energy outflows heat and scatter material, preventing new molecular clouds from forming. Energy exists, but in a destructive rather than generative role. Optical, radio, X-ray, and infrared comparisons make the contrast undeniable. Active spirals are dense, glowing, continuous in structure and star-forming activity. The Death Star galaxy is fragmented, depleted, and disrupted. Arms are skeletal, clusters isolated, molecular gas thin, dust patchy, and high-energy outflows prevent recovery. These comparisons highlight the unique, deathly characteristics that define the galaxy, setting it apart from peers that continue to thrive. Rotation and dynamics further reinforce the difference. Active spirals maintain ordered orbits for both stars and gas, facilitating the collapse of clouds into new stars. In the Death Star galaxy, outer disk filaments drift irregularly, gas moves misaligned with spiral arms, and high-velocity flows indicate stripping. Motion that supports life in other spirals contributes to decline in this galaxy, emphasizing depletion and disruption. Even subtle details of structure reveal differences. In star-forming galaxies, spiral arms are continuous ribbons, clusters aligned along gas lanes, molecular clouds dense and vibrant, dust thick and structured, energy balanced to sustain formation. In the Death Star galaxy, arms are interrupted, clusters isolated, clouds weak, dust patchy, and high energy flows destructive. The comparison shows a galaxy alive in form but dead in function, highlighting the absence of star formation, the depletion of cold gas, and the effect of disruptive high-energy phenomena. The science behind its death. The Death Star galaxy is not just fading, it is being quietly, relentlessly extinguished by forces beyond itself. The main theory that astronomers focus on is called cosmic starvation, sometimes described as galactic strangulation. Unlike catastrophic collisions or violent explosions, this process is subtle, almost invisible, yet devastating. It begins not with fire or shock waves, but with a slow removal of the galaxy's life-giving material, leaving behind a structure intact in shape but hollowed in function. Cosmic starvation occurs when a galaxy is cut off from the reservoirs of cold gas it needs to form new stars. Galaxies are not isolated. They exist within a vast network of intergalactic filaments, streams of gas and dark matter that feed them over millions or billions of years. Active galaxies tap into these flows, replenishing the gas lost to star formation or energetic outflows from their cores. In the Death Star galaxy, this connection has been severed. Hydrogen and molecular gas, normally abundant in spiral galaxies, are missing from much of the disk. Residual clouds exist only in scattered, isolated pockets. Without the inflow of fresh material, the galaxy can no longer replace gas consumed by previous generations of stars, leaving star formation to falter and eventually stop. Observations in multiple wavelengths reveal the mechanics of this starvation. Optical imaging shows spiral arms populated by older stars, but lacking the dense blue clusters typical of active regions. Radio observations confirm that neutral hydrogen is depleted, not evenly distributed along the arms, but fragmented into thin filaments drifting irregularly. ALMA measurements detect molecular clouds in tiny patches, but the density is insufficient to trigger large-scale star formation. X-ray data provides evidence of energetic phenomena, streams of radiation from the central core that interact with remaining gas, heating it and preventing condensation into new stars. The combination of depletion and disruption exemplifies the effects of cosmic starvation. The galaxy retains structure but is stripped of the material needed for life to continue. The strangulation is often gradual. In star-forming galaxies, gas accretion from the intergalactic medium balances the consumption of hydrogen and molecular clouds. The galaxy can sustain star formation for billions of years. In contrast, the Death Star galaxy shows signs that this supply was cut off at some point in its history. Gas reservoirs, once replenished by intergalactic filaments, have been exhausted, while high-energy outflows from the core scatter remaining clouds. Without inflow, the arms begin to fade, spiral structures lose brightness, and star clusters become isolated. The galaxy's life cycle slows, leaving only remnants of the activity that once made it vibrant. The process of galactic strangulation involves not only the removal of gas, but also the suppression of inflows from the environment. Intergalactic forces may disrupt the delicate connection between a galaxy and its cosmic surroundings. Streams of hydrogen and filaments of cold gas can be stripped away, diverted, or heated by nearby structures or energetic radiation. The Death Star galaxy shows evidence that such forces are at work. Its outer disk is depleted of gas, with filaments drifting irregularly. Molecular clouds fail to align with spiral arms. The galaxy is slowly strangled, unable to access the material it needs, leaving its star formation faltering and eventually ceasing. High-energy outflows play a critical role in this process. Observations show faint but persistent X-ray streams moving from the central core into the inner disk. These outflows do not destroy the structure, but prevent remaining gas from forming stars. Radiation heats the clouds, disperses molecular gas, and interacts with residual hydrogen, effectively sterilizing pockets that might have otherwise sparked new clusters. The combination of depletion and energetic interference ensures that once the galaxy loses access to intergalactic material, recovery becomes nearly impossible. Cosmic starvation is reinforced by these internal dynamics. The galaxy is deprived externally and disrupted internally, a dual mechanism that accelerates its decline. Comparisons with similar galaxies undergoing star formation clarify the impact of cosmic starvation. Active spirals of comparable mass and size continue to accrete gas from the intergalactic medium. Filaments feed the disk, molecular clouds remain dense, and star clusters form continuously along spiral arms. Their central cores emit energy that complements star formation rather than suppressing it. In the Death Star galaxy, the opposite occurs. The inflow of gas is cut off, molecular clouds are thin and fragmented, and high-energy outflows disrupt remaining gas. Spiral arms lose brightness, clusters become isolated, and star formation stalls. The contrasts are stark, revealing a galaxy that retains its shape but has lost its ability to sustain life. The mechanics of intergalactic stripping contribute to the galaxy's death. Observations suggest that tidal interactions, minor mergers, or even motion through a denser intergalactic medium can remove gas from the outer disk. Streams of hydrogen are pulled away, filaments scattered, molecular clouds disrupted. Unlike catastrophic collisions that destroy structure, these forces remove only the fuel for star formation, leaving the skeleton of the galaxy intact. The Death Star galaxy shows evidence of such interactions. Outer arms depleted, gas filaments misaligned, star clusters isolated. The stripping of material from the periphery reinforces the effect of cosmic starvation and accelerates the decline of stellar activity. Timescales for this process are vast. Star formation does not halt instantly. As the inflow of gas declines, the galaxy consumes what remains, generating new stars at a slower and slower rate. High-energy outflows from the core further prevent efficient collapse of molecular clouds. Over millions of years, spiral arms fade, star clusters dwindle, and the disk becomes a ghostly structure. Unlike galaxies quenched by collisions, which may experience immediate bursts of activity or destruction, the Death Star galaxy fades quietly, stripped and starved by the environment and its internal processes. Gas depletion is particularly striking. Observations reveal that the inner disk, which normally hosts molecular clouds and star-forming regions, has low-density hydrogen filaments, often drifting away from the spiral arms. ALMA images show molecular clouds confined to small, isolated patches. These clouds are insufficient for large-scale star formation. In active galaxies, molecular gas forms continuous lanes along the spiral arms, collapsing into new clusters. In the Death Star galaxy, The absence of dense lanes leaves only fragments. High-energy outflows prevent these fragments from collapsing further, effectively sterilizing the environment. The galaxy's decline is visible in the absence of new stars, a direct effect of cosmic starvation and intergalactic stripping. Environmental forces beyond the galaxy accelerate the process. The Death Star galaxy is embedded in a cosmic web of dark matter and gas filaments. In some regions, interactions with nearby galaxies or dense intergalactic gas can strip residual hydrogen and disrupt inflows. Observations suggest that the galaxy may have passed through a denser region of intergalactic medium or experienced tidal interactions that removed outer gas. These external forces prevent replenishment, ensuring that the galaxy cannot recover its ability to form stars. The combined effect of internal disruption and environmental isolation is what gives the galaxy its deathly status. High-energy outflows are another piece of the puzzle. X-ray imaging reveals irregular streams extending from the core into the inner disk. Unlike star-forming spirals where energy complements inflow and star formation, in the Death Star galaxy, these outflows heat residual gas, disperse molecular clouds, and suppress new clusters. Optical imaging shows faint blue clusters only in isolated pockets, evidence that any residual star formation is rare and weak. Radio observations show hydrogen filaments fragmented and irregular, drifting away from the disk. Infrared imaging highlights thin dust lanes around residual clouds, but no continuous lanes capable of sustaining star formation. Together, these multi-wavelength observations illustrate how internal high-energy activity reinforces cosmic starvation. The combination of depleted gas, disrupted molecular clouds, and high-energy outflows provides a comprehensive picture of galactic strangulation. Spiral arms fade, star clusters shrink and become isolated, and star formation stalls. Unlike violent quenching from collisions or mergers, the Death Star galaxy experiences a slow, relentless decline. Its skeleton remains intact, and its spiral structure persists, but the life processes that once sustained it are gone. Cosmic starvation is a subtle killer, invisible at first glance but devastating over millions of years. Galactic strangulation also interacts with the galaxy's rotation and orbital dynamics. Stars in the core continue to follow regular paths anchoring the central mass. Outer disk gas and residual molecular clouds, however, move irregularly. Filaments drift misaligned with the spiral pattern, high-velocity flows strip remaining material, and interactions with intergalactic forces prevent replenishment. While active spirals maintain ordered rotation that supports gas inflow and star formation, the Death Star galaxy shows disruption at multiple levels, reinforcing the effect of cosmic starvation. The galaxy's environment plays a role in maintaining its deathly state. Unlike isolated spirals that continue to accrete gas from intergalactic filaments, the Death Star galaxy may reside in a region where inflows are blocked or diverted. Nearby structures, dense intergalactic gas, or past tidal interactions prevent gas replenishment. Without the ability to replace consumed material, star formation stalls, molecular clouds dissipate, and spiral arms fade. The galaxy remains a visible spiral, but is functionally dead in terms of ongoing stellar creation. Even small residual gas pockets struggle to generate new stars. High-energy outflows from the core heat molecular clouds, preventing gravitational collapse. Thin dust lanes visible in infrared light trace only the most isolated remnants of star-forming material. Spiral arms, while intact, host few young clusters scattered across the disk in isolation. Optical images reveal dim, faint patches of blue light, evidence of minor, intermittent formation in an otherwise dying environment. The Death Star galaxy illustrates a combination of processes that lead to its demise. Cosmic starvation cuts off inflows of gas, intergalactic forces strip residual material from the outer disk, and high-energy outflows from the core prevent new stars from forming. Spiral arms remain skeletal, molecular clouds are thin and sparse, dust lanes fragmented, and star clusters isolated. Multi-wavelength observations converge on a single conclusion. The galaxy retains shape but has lost function. Its death is not explosive. It is a slow, quiet starvation, a strangulation that stretches across millions of years, stripping the galaxy of its ability to sustain life. The invisible forces killing galaxies. The universe is not empty. Between galaxies, there exists a vast invisible network known as the cosmic web. Think of it as a gigantic three-dimensional spiderweb stretching across billions of light years. The strands of this web are made of gas, dust, and dark matter, connecting galaxies to one another. These filaments feed galaxies with the material needed to create new stars, while vast empty spaces called voids lie between the filaments, regions almost entirely devoid of matter. Galaxies like the Death Star galaxy exist within this cosmic web, and their survival depends on the invisible flows of gas that travel along its filaments. When a galaxy is healthy, cold gas flows from the cosmic web into the galaxy's disk. This gas collects in dense clouds, collapsing under gravity to ignite new stars. These clouds are the raw material for life inside a galaxy. But if these flows are cut off, star formation begins to falter. Without a steady supply of cold gas, galaxies can slowly run out of fuel, entering a state scientists call cosmic starvation. The role of voids is equally important. Imagine floating in a vast desert, far from any oasis. Voids are like these deserts in space. They contain very little gas, very little matter, and they create regions where galaxies are isolated from fresh supplies. When a galaxy drifts into or near a void, its access to the filaments of the cosmic web can be blocked or disrupted. Without gas flowing in from the web, the galaxy loses its ability to form new stars. Spiral arms, once bright with clusters of young stars, begin to fade. Star formation slows, clusters become isolated, and over millions of years, the galaxy can appear alive in shape but dead in function. Filaments act like cosmic highways for gas. They are long, thread-like structures filled with both visible gas and invisible dark matter. Galaxies tap into these filaments to refill their supply of star-forming material. When a galaxy is connected to multiple filaments, it can continue forming stars for billions of years. But the Death Star galaxy, according to observations, seems disconnected from its filaments. Streams of hydrogen and molecular gas no longer flow into the disk. The spiral arms, once nourished by these cosmic highways, now only host scattered faint clusters of stars. Hot gas also plays a hidden but deadly role. Surrounding many galaxies is a halo of hot gas, millions of degrees in temperature. While cold gas fuels star formation, hot gas can prevent it. If the surrounding gas is heated, new inflows from filaments cannot cool and condense to form molecular clouds. Essentially, the galaxy becomes surrounded by a suffocating blanket of heat. High-energy radiation, both from the galaxy's central core and from intergalactic space, can keep gas in this hot state, preventing it from feeding star formation. Even small pockets of cold gas are heated and dispersed, leaving the galaxy without the fuel it needs. Dark matter is another invisible player in this cosmic story. While we cannot see dark matter directly, it exerts gravitational forces that shape the structure of the cosmic web. Filaments of dark matter pull gas along them, directing flows toward galaxies. They also affect the motion of galaxies themselves, influencing how they move through voids or along the web. In the Death Star galaxy, dark matter may play a dual role. It maintains the galaxy's spiral structure and gravitational integrity, while simultaneously allowing external forces to strip gas away. Streams of gas moving along dark matter filaments may be diverted, preventing replenishment. In effect, dark matter creates the scaffolding for life, but also shapes the path of the galaxy's slow death. The interplay of these forces, cosmic web, voids, filaments, hot gas, and dark matter, determines a galaxy's fate. Galaxies that remain connected to dense filaments with steady inflows of cold gas continue forming stars and thriving. Galaxies near voids, cut off from these flows, slowly lose their fuel. Hot gas halos prevent replenishment, high-energy outflows disrupt residual clouds, and dark matter guides the remaining gas in ways that may limit recovery. The result is a galaxy that keeps its spiral arms and central core, but loses the ability to produce new stars. a skeletal structure surrounded by emptiness. Observations of other galaxies in similar cosmic neighborhoods reinforce this picture. Star-forming spirals in filament-rich regions glow brightly with young blue clusters along their arms. Their disks are filled with molecular clouds, dense hydrogen filaments, and dust lanes that feed continuous star formation. In contrast, galaxies in sparse or void-dominated regions show fragmented arms, depleted molecular gas, and irregular gas flows. Spiral arms are faint, clusters are isolated, and new stars are rare. The Death Star galaxy fits perfectly into this latter category, illustrating the deadly effect of being starved by its cosmic environment. Multi-wavelength observations provide a layered view of these processes. In optical light, spirals glow where stars are forming, while voids create regions of darkness. Radio observations map the hydrogen distribution along filaments, showing which galaxies are being fed and which are isolated. X-ray imaging detects hot gas halos and high-energy outflows that disrupt remaining star-forming clouds. Infrared imaging traces dust heated by stellar activity or energetic radiation. Combining these perspectives shows a clear pattern. Galaxies connected to the cosmic web thrive. Those cut off slowly die. The Death Star galaxy's environment illustrates how these processes intersect. Its outer disk shows depleted hydrogen filaments, irregular molecular clouds, and thin dust lanes. X-ray streams extend from the central core into the inner disk, heating gas and suppressing collapse. The galaxy's spiral arms are intact but faint, a skeleton of what was once vibrant. Observations suggest that the galaxy's filaments have been severed. It has drifted near a void, and its hot gas halo prevents replenishment. Dark matter provides gravitational support, but cannot replace the missing fuel. Star formation is nearly extinct, leaving only isolated pockets of residual activity. The effect of voids is particularly dramatic. These vast empty regions can act like cosmic deserts, cutting off galaxies from the lifeblood of intergalactic gas. A galaxy drifting into or near a void finds fewer inflows along filaments. Hydrogen that once flowed smoothly into the disk is now scarce, scattered, or moving in irregular paths. Molecular clouds become isolated and weak, dust lanes thin and fragment, spiral arms fade, and clusters become scattered islands rather than continuous chains. Over millions of years, the galaxy fades, its skeletal structure intact but functionally dead. Filaments themselves are fragile highways. Gas traveling along them is influenced by dark matter, gravitational interactions with nearby galaxies, and environmental factors such as hot gas. Even slight perturbations can divert gas away from the galaxy, depriving it of fuel. The Death Star galaxy appears to have lost its filamentary connections. Observations of hydrogen show thin, fragmented streams, molecular clouds in tiny patches, and irregular gas flows. Without a steady supply of inflowing gas, star formation cannot continue, and the spiral arms slowly lose vitality. Hot gas halos magnify this effect. Surrounding the galaxy, a diffuse cloud of hot gas prevents inflows from cooling sufficiently to form stars. Any residual molecular clouds are disrupted by heat, X-ray radiation, or pressure from the surrounding medium. In effect, the galaxy is trapped inside a warm, hostile environment, unable to access the cold material needed for new stars. Unlike catastrophic events that destroy a galaxy in an instant, this heating works quietly, maintaining a slow, relentless suppression of star formation over millions of years. Dark matter, invisible but powerful, plays a subtle role. Filaments of dark matter guide gas flows and shape galaxy motion. They provide gravitational support to the disk, maintaining the spiral arms and central core. At the same time, they influence the motion of gas around the galaxy. Streams of hydrogen that might once replenish the disk can be diverted along the gravitational scaffolding, reinforcing the effects of cosmic starvation. Dark matter is both the structure that holds the galaxy together and part of the mechanism that prevents recovery. The combined impact of cosmic web disconnection, void proximity, disrupted filaments, hot gas halos, and dark matter effects creates a galaxy in slow decline. Star formation, The life-giving process for spirals is nearly extinct. Molecular clouds fragment, hydrogen is depleted, dust lanes thin, and X-ray streams prevent new clusters from forming. Spiral arms remain, central cores persist, but the galaxy's vitality is gone. Multi-wavelength observations, optical, radio, X-ray, and infrared, reveal the invisible forces at work, providing a comprehensive picture of galactic death by environmental starvation. Even small differences in environment can make the difference between a thriving galaxy and a dying one. Galaxies with rich filament connections continue to form stars along their spiral arms. Those near voids or with severed inflows, like the Death Star galaxy, slowly fade. The hot gas surrounding them prevents replenishment, and dark matter channels remaining gas in ways that reinforce depletion. Over millions of years, the spiral arms become skeletal, clusters isolated, and star formation nearly extinct. Cosmic context, the universe's role. The Death Star galaxy does not exist in isolation. Its decline is part of a much larger tapestry, one that stretches across millions of light years, connecting galaxies through invisible threads and vast empty spaces. The galaxy's death is not just an internal story of depleted gas and fading stars. It is a product of the universe itself, its structure, forces, and the invisible currents that flow through cosmic space. Understanding its demise requires looking beyond the galaxy, into the cosmic context that shapes its fate. One of the most critical players is the intergalactic medium, the thin, diffuse gas that fills the space between galaxies. It is not empty, though it may seem so. This medium carries the hydrogen, helium, and other elements that fuel star formation in galaxies. It flows through the cosmic web along filaments, connecting galaxies like arteries of life in a vast network. For galaxies connected to dense regions of this medium, inflows replenish molecular clouds, support star formation, and maintain the rhythm of growth. The Death Star galaxy, however, shows evidence that these flows are blocked or redirected. Streams of intergalactic gas that would normally nourish the disk are scarce or misaligned, leaving the galaxy isolated and starving. The cosmic web itself, the intricate network of filaments and voids, plays a defining role. Filaments are the highways of the universe, channels along which gas, dust, and even dark matter travel. They funnel material into galaxies, providing the continuous supply required to sustain star formation. In contrast, voids are enormous regions of near-empty space, deserts in the cosmic landscape. When a galaxy drifts near or into a void, these channels become fragmented or inaccessible. The Death Star galaxy, based on observations, appears to inhabit such a precarious position. Its connections to filaments have weakened, and voids surround it, isolating it from the life-giving streams of gas that could sustain star formation. Gravity acts as both a shaper and a sculptor in this context. It organizes the large-scale structure of the universe, dictating the flow of matter along filaments and the formation of clusters of galaxies. Dark matter, invisible yet dominant, reinforces this structure. Its gravitational pull guides gas along filaments, shapes galaxy orbits, and provides the scaffolding upon which cosmic architecture is built. For the Death Star galaxy, gravity and dark matter define the paths of inflowing gas and the trajectories of material being stripped away. Streams that might have nourished the galaxy are diverted or dispersed along gravitational paths, leaving the disk depleted and star formation suppressed. The intergalactic medium also interacts dynamically with the galaxy. As the Death Star galaxy moves through this medium, external pressure and interactions can strip residual gas from its outer disk. This is not a sudden, violent collision, but a steady erosion, a friction between the galaxy and the surrounding material. Outer gas filaments become detached, molecular clouds are scattered, and dust lanes thin. The interplay of the galaxy's motion, the surrounding medium, and gravitational forces ensures that recovery is difficult. Even if some gas remains, high-energy processes prevent it from condensing into new stars. The universe, through its intergalactic medium, effectively throttles the galaxy's ability to sustain itself. Filaments not only supply gas, but also carry dark matter, anchoring galaxies within the cosmic web. In healthy star-forming galaxies, these filaments deliver a steady inflow of material along gravitational channels. In the Death Star galaxy, the connections are weak or broken. Hydrogen streams are thin and fragmented. Molecular clouds are confined to small isolated patches. Dust lanes are sparse. The galaxy is structurally intact, but the cosmic web no longer nourishes it. Star formation stalls, clusters become isolated, and spiral arms fade. The universe, in this sense, exerts its influence silently but inexorably. Voids, conversely, act as barriers. The empty space surrounding the Death Star galaxy prevents replenishment from reaching the disk. Cold gas cannot flow in, molecular clouds cannot form, and star clusters are limited to residual material. The galaxy is trapped, caught between depleted filaments and surrounding voids. Unlike galaxies in denser filament networks, it cannot tap into streams of inflowing gas. The universe's structure through these voids has effectively isolated it, turning what might have been a vibrant spiral into a skeletal remnant. Gravity and dark matter reinforce this isolation. The dark matter halo surrounding the galaxy maintains its shape, keeping the spiral arms intact and preserving orbital patterns. But these gravitational forces also channel surrounding gas along paths that do not replenish the galaxy's disk. Streams that might have fueled star formation are diverted or prevented from cooling. The result is a galaxy structurally sound but starved at its core. In this way, gravity and dark matter both support the galaxy's form and contribute to its functional death. Hot gas in the surrounding environment adds another layer of influence. Many galaxies are enveloped by halos of hot, diffuse gas. In galaxies still forming stars, this gas cools as it flows inward, condensing into molecular clouds that fuel new clusters. In the Death Star galaxy, the surrounding hot gas remains heated, preventing inflows from cooling. Any residual molecular clouds inside the disk are disrupted by interactions with this high-energy environment. Star formation cannot resume. The galaxy becomes an island of structure in a sea of energy that suppresses growth. Interplay between filaments, voids, hot gas, and dark matter shapes the galaxy's slow decline. The Death Star galaxy is cut off from the flows that sustain star formation, isolated by voids, disrupted by hot gas, and influenced by dark matter in ways that divert the remaining fuel. Spiral arms remain as visual remnants, but clusters are isolated and sparse. Molecular clouds are weak, hydrogen filaments are fragmented, and dust lanes are thin. The universe itself orchestrates the galaxy's decline, creating the perfect conditions for slow, inevitable starvation. Even at a larger scale, the cosmic environment affects timing. Galaxies in rich filamentary networks continue to form stars for billions of years, replenished continuously by inflows along multiple channels. Galaxies near voids like the Death Star galaxy face long-term suppression. Their gas supply dwindles, molecular clouds dissipate, and spiral arms fade over millions of years. Multi-wavelength observations, optical, radio, X-ray, infrared, reveal these processes clearly. Spiral arms glow in star-forming galaxies, but in isolated galaxies, faint arms and scattered clusters dominate the disk. The Death Star galaxy exemplifies how intergalactic phenomena dictate fate. Its decline is not caused by collisions or internal explosions alone. The universe itself, the intergalactic medium, cosmic filaments and voids, gravity and dark matter, plays a central role. Streams of inflowing gas are blocked or diverted. The surrounding medium strips residual material. Dark matter shapes the motion of gas. Hot gas prevents cooling. Over millions of years, star formation slows and eventually nearly ceases, leaving a spiral structure hollowed of life. Observations across multiple wavelengths show the delicate balance of these forces. Optical images reveal spiral arms with few remaining clusters. Radio maps show fragmented hydrogen filaments. X-ray observations highlight hot gas that prevents residual clouds from collapsing. Infrared imaging traces dust that is patchy and faint, unable to sustain star formation. Combined, these data paint a picture of a galaxy whose fate is determined as much by the universe itself as by internal dynamics. Even subtle gravitational interactions can make a difference. Tidal forces from nearby galaxies, the pull of dark matter filaments, or motion through the intergalactic medium can remove gas from the outer disk. Streams of hydrogen that might have fed star formation are stripped or diverted. Molecular clouds drift away from spiral arms. Dust lanes thin. Star clusters are left isolated. The universe's large-scale structure actively shapes which galaxies thrive and which fade, determining the longevity of star formation. The Death Star galaxy's position in the cosmic web is critical. Isolated in a low-density region, surrounded by voids, and cut off from robust filaments, the galaxy experiences slow starvation. Hot gas halos prevent cooling inflows. Dark matter channels remaining gas along paths that do not replenish the disk. High-energy outflows from the central core disrupt any residual material. The galaxy maintains its shape but loses its ability to produce new stars. Its spiral arms remain visible, but the disk is effectively dead. The long-term fate of dying galaxies, life and death on cosmic scales. Galaxies are not eternal. They are born, grow, thrive, and eventually fade, caught in a rhythm dictated by both their internal fuel and the environment around them. The Death Star galaxy represents one of the most extreme cases. A galaxy whose star formation has nearly ceased, leaving it structurally intact, but functionally lifeless. Its long-term fate is tied to universal processes operating over billions of years, processes that govern the evolution of galaxies across cosmic history. When a galaxy loses its ability to form new stars, it enters a phase that astronomers refer to as quenching. This is the stage in a galaxy's life cycle when stellar birth slows dramatically or stops entirely. Unlike galaxies that maintain vigorous star formation for billions of years, quenched galaxies gradually fade, their disks filled with aging stars and increasingly sparse molecular clouds. Their spiral arms lose brightness. The young blue clusters disappear, and only older, redder stars dominate the visual light. Over time, the lack of new stars means that the galaxy's overall luminosity diminishes, making it appear ghostly, even if its overall mass remains unchanged. The Death Star galaxy is a prime example of this process in action. With its cold gas depleted, molecular clouds fragmented, and star formation stalled, the galaxy is entering a stage where internal processes can no longer reverse its decline. Unlike catastrophic collisions that immediately disrupt structure, this kind of slow quenching preserves the galaxy's shape while stripping it of vitality. The spiral arms remain visible, the central core retains mass, and the overall disk continues to orbit, but the galaxy has effectively lost the ability to generate new life in the form of stars. In terms of the long-term cosmic evolution, such galaxies are destined to join the population known as red and dead galaxies. These are systems dominated by older red stars, lacking the blue, high-mass stars that define active star formation. Over billions of years, even these older stars will age and die, producing planetary nebulae or collapsing into white dwarfs. Supernovae will continue to occur, but at a dwindling rate. Eventually, the galaxy's luminosity will fade, leaving behind a quiet structure composed of dim, long-lived stars. In essence, the galaxy becomes a fossil, a record of a once active system frozen in a state of arrested growth. Galaxies like the Death Star galaxy are rare, but not unique. Surveys of the local universe show that a small fraction of galaxies have undergone this extreme quenching, particularly in regions where the cosmic environment prevents replenishment of cold gas. These systems are more likely to be found in low-density regions, where inflows from cosmic filaments have been severed, or in cluster environments, where interactions with hot intracluster gas and gravitational forces strip away remaining material. While most galaxies retain at least some star formation over billions of years, galaxies facing both internal depletion and external environmental pressures follow this slower, inevitable path toward death. The rarity of this phenomenon makes it a compelling case study. Active star-forming spirals dominate the observable universe, glowing with blue clusters, dense molecular clouds, and vibrant disks. In contrast, galaxies undergoing this kind of cosmic starvation are visually striking because of the contrast. A galaxy that appears structurally intact but behaves like a fossil. Multi-wavelength observations reveal their unique characteristics: thin, fragmented gas filaments, isolated molecular clouds, and faint, aging clusters scattered across the disk. Their existence highlights how environment, cosmic position, and internal processes combine to determine a galaxy's life trajectory. Understanding the life cycle of galaxies on cosmic scales requires looking at both ends of the spectrum: active, thriving galaxies and quenched, dying systems. Galaxies are born in dense regions of the early universe, forming from clouds of gas and dust in gravitational wells sculpted by dark matter. Initially, star formation is rapid, fueled by abundant molecular gas and inflows along cosmic filaments. Over time, galaxies grow, their disks expanding, spiral arms developing, and star clusters forming in abundance. Many maintain this vibrant stage for billions of years, sustained by continuous gas replenishment from the intergalactic medium. Eventually, however, a galaxy's environment and internal processes determine whether it continues to thrive or begins to decline. Interactions with voids, isolation from filaments, heating by surrounding gas, and gravitational influences of dark matter can gradually sever inflows, leading to the slow quenching seen in galaxies like the Death Star galaxy. Others may undergo more violent processes, such as collisions or mergers, which can trigger starbursts before ultimately exhausting their fuel. Regardless of the path, the universal life cycle remains consistent: birth, growth, active life, quenching, and eventual fading into cosmic silence. The long-term fate of galaxies like the Death Star galaxy is particularly striking in its quiet inevitability. Unlike galaxies destroyed in collisions, which can be violently reshaped, these star-depleted systems remain intact for billions of years. Spiral arms persist, central bulges hold their mass, and orbital patterns of existing stars continue, maintaining structure even as vitality fades. Over cosmic timescales, the faint aging stars dominate, supernova events become increasingly rare, and the galaxy transitions into a state of near-total inactivity. These systems, frozen in arrested evolution, become part of the universe's quiet majority, massive structures that occupy space but contribute little to ongoing star formation. At a cosmic scale, the death of individual galaxies is part of the universe's evolving landscape. Star formation is the process that drives chemical enrichment, planetary system creation, and the ongoing generation of luminous energy across the cosmos. When galaxies like the Death Star galaxy are removed from this cycle, it represents a shift in the cosmic balance. Regions of space become dominated by older stars, lacking the ongoing replenishment of light and heavy elements. The universe itself becomes progressively more static, with fewer active systems generating new stars. Studying galaxies like this also provides insight into the environmental conditions that shape cosmic evolution. They reveal the importance of intergalactic medium density, filament connectivity, and void proximity in determining whether a galaxy continues to form stars or enters a slow decline. Observations of hydrogen distribution, molecular cloud density, and high-energy outflows allow astronomers to reconstruct the processes leading to quenching. In this sense, each dying galaxy acts as a laboratory, illustrating the interplay between environment and galactic life cycles. The rarity of this phenomenon does not diminish its significance. While most galaxies retain active star formation for billions of years, the extreme cases reveal boundaries, the limits of cosmic inflows, the effects of isolation, and the impact of intergalactic pressures. They show that even structurally intact galaxies are vulnerable to environmental and internal forces, and that the universe can quietly enforce a galaxy's decline without catastrophic events. In the observable universe, such systems stand out as anomalies, demonstrating the range of galactic evolutionary pathways. The life cycle of galaxies also links to the broader picture of cosmic history. Early in the universe, star formation rates were higher, gas reservoirs abundant, and galaxies connected to multiple filaments. Over billions of years, some galaxies maintained these connections and thrived, while others became increasingly isolated, encountering voids or losing filament access. Environmental pressures, dark matter halos, and hot gas halos all influenced whether a galaxy remained active or gradually quenched. The Death Star galaxy exemplifies the endpoint of this process, a system structurally intact but star-depleted, a snapshot of what happens when environmental and internal forces align to halt cosmic creation. Over billions of years, the long-term evolution of these galaxies continues. They drift slowly through space, isolated from fresh gas, their stellar populations aging. Supernova rates diminish, molecular clouds dissipate, and remaining hydrogen filaments fade. Spiral structures may persist visually for a long time, but the galaxy becomes functionally silent. Over tens of billions of years, even these stars age, leaving white dwarfs and dim remnants, until the galaxy exists as a quiet fossil, a record of its past activity frozen in the cosmic web. Even though such galaxies are rare, they are crucial to understanding the full spectrum of galactic evolution. They illustrate how environmental conditions, cosmic structures, and internal depletion converge to shape a galaxy's life trajectory. By comparing these systems to thriving galaxies, astronomers can see how filaments, voids, intergalactic medium, and dark matter govern the cosmic ecosystem. Every dying galaxy is a reminder that structure alone does not guarantee life. The universe itself exerts influence, determining which galaxies thrive and which fade into quiet emptiness. Innovations enabling the detection of dying galaxies. The discovery of galaxies like the Death Star galaxy owes everything to decades of technological innovation. Detecting a galaxy in the final stages of its life is far from easy. These galaxies are faint, their star formation nearly extinct, and their gas reservoirs depleted. Observing them requires instruments that can capture light across the spectrum, from visible starlight to the cold hydrogen filaments that feed them, to the energetic X-rays and radio waves that reveal heating and outflows. The Hubble Space Telescope revolutionized our understanding of galaxies by giving astronomers unprecedented optical and near-infrared views. With its sharp imaging, Hubble could resolve individual star clusters in distant galaxies, revealing where star formation was ongoing and where it had slowed or stopped entirely. For galaxies like the Death Star galaxy, Hubble's observations showed faint aging clusters and spiral structures intact, but lacking new blue stars. This optical clarity allowed scientists to distinguish between active and quenched regions within the disk, mapping areas of residual star formation and identifying regions that had been completely shut down. Beyond optical imaging, Hubble's near-infrared instruments could peer through dust lanes, revealing the underlying structure of galaxies obscured in visible light. This capability was critical in identifying dying galaxies because even galaxies that appeared faint in optical light could still host pockets of hidden activity. Hubble's sensitivity to subtle differences in color and brightness allowed astronomers to classify galaxies along a continuum, from active spirals to quenched systems, providing the first clues that galaxies like the Death Star were not anomalies but part of a broader population, undergoing slow quenching. While Hubble mapped stars and dust, the James Webb Space Telescope, JWST, brought a new era of infrared observation. JWST can detect faint thermal emissions from the coldest dust and gas, tracing the molecular clouds where stars form or fail to form. For the Death Star galaxy, JWST observations highlighted areas where cold molecular gas was absent, showing the galaxy's disk had largely lost the raw material necessary for star formation. Its infrared spectrographs could detect faint traces of carbon monoxide and molecular hydrogen, revealing gaps in the galaxy's fuel supply. JWST also enabled astronomers to examine high-redshift galaxies, connecting the processes observed in local dying galaxies to similar trends in the early universe. Meanwhile, ALMA, the Atacama Large Millimeter-Submillimeter Array, provided a complementary perspective by mapping cold gas at unprecedented resolution. ALMA observes the universe in millimeter and submillimeter wavelengths, ideal for detecting molecular gas clouds invisible in optical light. For galaxies in the Death Star phase, ALMA revealed fragmented and depleted hydrogen filaments, isolated molecular clouds, and disrupted gas flows. These observations showed that the cessation of star formation was not uniform. Pockets of residual gas remained, but they were disconnected and insufficient to sustain new star formation. ALMA's sensitivity to cold gas was essential in confirming that galaxies were truly dying, rather than merely dim. Ground-based observatories also played a crucial role. The Vera Rubin Observatory, with its wide-field survey capabilities, allowed astronomers to monitor large populations of galaxies over time. Its ability to map the distribution of galaxies in clusters, filaments, and voids helped contextualize the Death Star galaxy within its cosmic environment. By comparing hundreds of thousands of galaxies, astronomers could identify those showing signs of quenching, understanding how environmental factors like void proximity and filament connectivity contributed to their decline. The observatory's time domain surveys also enabled tracking changes in brightness and activity, giving insight into the slow, gradual nature of galactic death. Other multi-wavelength facilities complemented these efforts. Radio telescopes mapped the neutral hydrogen content of galaxies, highlighting regions depleted of cold gas. Observations in X-ray wavelengths captured high-energy outflows, hot gas halos, and interactions with the intergalactic medium, all of which could suppress star formation. Infrared and submillimeter arrays traced dust heating and residual molecular clouds, providing a comprehensive view of a galaxy's internal state. By combining these datasets, astronomers could identify galaxies transitioning from active star formation to quiescence, creating a detailed picture of dying galaxies across the universe. Technological innovations extended beyond individual instruments to survey design and data processing. Massive sky surveys like Sloan Digital Sky Survey, SDSS, provided catalogues of galaxies with detailed photometric and spectroscopic measurements. These data allowed astronomers to calculate star formation rates, gas content, and environmental density for vast populations of galaxies. Advanced software pipelines and machine learning algorithms then sifted through these datasets, identifying subtle indicators of quenching. The Death Star galaxy's unusual properties, its depleted gas, faint star clusters, and isolation, could only be detected because these surveys offered both breadth and precision. The integration of multi-wavelength data transformed galaxy studies. Optical telescopes revealed star clusters and spiral structure. Infrared instruments traced cold dust and obscured molecular clouds. Radio arrays mapped hydrogen distribution, and X-ray facilities highlighted hot gas halos and energetic outflows. Individually, each instrument provided a partial picture. Together, they allowed astronomers to see the full life cycle of galaxies, including those in the final stages of quenching. Observations of the Death Star galaxy drew on this synergy, combining data across wavelengths to confirm that its star formation was nearly extinct and that environmental factors played a major role. Space-based and ground-based observatories also brought improvements in spatial resolution and spectroscopic capability. Resolving individual clusters, mapping gas filaments, and detecting faint emissions required extreme precision. Instruments like JWST's NIRSPEC could split light into detailed spectra, revealing chemical composition, temperature, and density of residual gas. ALMA's interferometry provided spatial resolution down to tens of parsecs, enabling scientists to see how molecular clouds were fragmented or misaligned. These innovations allowed astronomers to understand not just that a galaxy was dying, but why it was dying. Survey coordination became another innovation. By combining observations from Hubble, JWST, ALMA, Vera Rubin Observatory, and other facilities, astronomers could create comprehensive, layered datasets. Optical imaging showed stellar populations. Infrared revealed dust and hidden star formation. Submillimeter mapping traced molecular gas. And X-ray observations revealed energetic processes. This coordinated approach allowed researchers to study galaxies in their full cosmic context, linking internal quenching processes to environmental influences. Data analysis itself advanced dramatically. Processing large multi-wavelength datasets required sophisticated algorithms capable of detecting faint signatures, separating noise, and identifying subtle trends. Machine learning models could recognize patterns in star formation, gas depletion, and dust distribution, highlighting galaxies in transition. The Death Star galaxy stood out in these analyses because of its combination of faint optical clusters, fragmented molecular clouds, and depleted gas filaments. Without these innovations in both instrumentation and computational analysis, such galaxies might have remained invisible. Even timing innovations played a role. Repeated observations over months and years allowed astronomers to track changes in residual gas, detect inflows or outflows, and study high-energy phenomena. Time domain data provided dynamic insights into processes that operate on timescales of millions of years. Observatories like Vera Rubin enabled these long-term studies, mapping how the galaxy's star formation declined gradually rather than suddenly. The combination of sensitivity, resolution, multi-wavelength coverage, survey breadth, and computational analysis represents a new era in galactic astronomy. Detecting dying galaxies requires all these capabilities working in concert. Observatories like Hubble and JWST reveal the stellar skeleton and residual dust. ALMA traces cold gas. Vera Rubin Observatory and large surveys provide context. Radio and X-ray facilities capture interactions with the intergalactic medium. Advanced algorithms process massive datasets, highlighting rare, extreme cases of quenching. Together, these innovations allow astronomers to study the Death Star galaxy and others like it in unprecedented detail, uncovering the processes that quietly end a galaxy's star formation. Even more specialized instruments contribute. Integral field units, spectrographs, and adaptive optics systems enhance the resolution of distant galaxies, allowing the mapping of velocity fields, gas flows, and star formation histories. Observing the kinematics of stars and gas in dying galaxies provides insight into how material is redistributed during quenching, revealing interactions with environmental forces and internal dynamics. These observations confirm that galaxies like the Death Star are not simply underluminous, but are undergoing a complex interplay of suppression, isolation, and depletion. The combination of wide surveys and deep targeted observations is crucial. Broad surveys identify candidate galaxies showing signs of quenching across cosmic volumes, while detailed observations with high-resolution instruments confirm the mechanisms responsible. The Death Star galaxy was first flagged by its faint star-forming regions in optical surveys, then examined with JWST, ALMA, and X-ray observatories to map gas depletion and hot halos. Only through this multi-layered approach could astronomers assemble the full picture of its dying state. In recent years, innovations in data visualization and simulation have further enhanced understanding. 3D reconstructions of galaxies and their surrounding filaments allow scientists to see how gas flows along the cosmic web, how voids limit inflows, and how hot gas and dark matter shape star formation. Simulations of galaxy evolution, calibrated with multi-wavelength observations, enable researchers to predict the trajectory of dying galaxies, linking observed states to long-term outcomes. For the Death Star galaxy, these models suggest its gas depletion is permanent, confirming its status as a quenched system. Collaborations across observatories, institutions, and continents have transformed the field. No single telescope can capture the full picture. Only by combining resources, Hubble for optical clarity, JWST for infrared depth, ALMA for cold gas mapping, Vera Rubin for surveys, and X-ray observatories for energetic processes, can astronomers detect and study galaxies in extreme quenching phases. These collaborative innovations have turned galaxies like the Death Star from invisible anomalies into detailed case studies, revealing the hidden processes that control their evolution. Seeing galaxies die, light, gas, motion, and cutting-edge technology. Observing a galaxy in the final stages of its life is like trying to read the faint heartbeat of a distant star. Galaxies are massive, sprawling structures, yet the processes that end their star formation occur subtly over millions of years, hidden in cold clouds, faint stellar remnants, and delicate flows of gas. Detecting these signals requires sophisticated instruments capable of tracing the faintest emissions, mapping invisible gas, and capturing the motion of stars and clouds in exquisite detail. Light is the first clue. Telescopes like the Hubble Space Telescope collect photons emitted by stars across vast distances. In a dying galaxy, bright blue stars are missing, leaving only older, redder stars. Optical imaging captures this shift in color and intensity. Spiral arms may still be visible, but the glow is softer, dotted with aging clusters, rather than newborn stars. These subtle differences in light tell astronomers that star formation is slowing or has nearly stopped. Infrared observations add another layer of insight. Dust within galaxies absorbs visible light and re-emits it in the infrared. Instruments like the James Webb Space Telescope detect this faint infrared glow, revealing regions of molecular clouds that may still host star formation, or confirming their absence. In the Death Star galaxy, infrared mapping shows sparse, fragmented clouds, evidence that the fuel for new stars is largely gone. Infrared also penetrates dense dust lanes that optical light cannot, exposing the hidden skeleton of the galaxy. Gas is the lifeblood of galaxies, and mapping it is essential to understanding why a galaxy is dying. Radio and submillimeter observatories like ALMA trace cold molecular gas, primarily hydrogen, the raw material for star formation. In healthy galaxies, dense filaments of hydrogen feed the disk, creating stars along spiral arms. In dying galaxies, ALMA detects a fragmented, depleted distribution, thin, isolated patches of gas instead of continuous flows. These observations make it clear that the galaxy's star-forming machinery has been shut down at its source. Hot gas surrounding galaxies tells a different story. X-ray observatories detect energetic emissions from gas heated by supernovae, active galactic nuclei, or the intergalactic medium. For dying galaxies, X-ray maps reveal halos of hot gas that prevent remaining cold gas from condensing into new stars. Streams of molecular clouds may be disrupted, and energy from the central core can create outflows that remove gas from the disk. Observing these high-energy processes explains why quenching is not just about depletion, but also about ongoing suppression of star formation. Motion within the galaxy is equally important. Spectral mapping allows astronomers to measure the velocities of stars and gas, revealing how material moves through the disk and how inflows or outflows are disrupted. By splitting light into detailed spectra, spectrographs detect Doppler shifts, showing whether clouds are moving toward or away from the observer. In dying galaxies, these measurements often show fragmented motions, gas clouds being stripped, or residual inflows too weak to fuel new star formation. Spiral arms may rotate normally, but the flows that once fed star formation are weakened or misaligned. Spectral mapping is a cornerstone of modern galactic astronomy. It goes beyond simply detecting light. It provides a full three-dimensional view of the galaxy's structure and dynamics. Each wavelength, each spectral line traces a different component. Hydrogen emission lines reveal cold gas, oxygen and carbon lines trace star-forming regions, and absorption lines highlight older stellar populations. By combining these observations, astronomers can create detailed maps showing which parts of the galaxy are active, which are passive, and how the remaining gas moves or fails to move. Simulations complement observations, offering a way to visualize processes that occur over millions of years. Computational models of galaxy evolution incorporate gravity, gas physics, dark matter, and intergalactic interactions to predict how a galaxy's star formation will change over time. By inputting parameters observed in dying galaxies, such as gas depletion, hot gas halos, and weak inflows from cosmic filaments, simulations can reproduce the slow quenching seen in systems like the Death Star galaxy. These models reveal the underlying mechanics, how isolation from the cosmic web, interactions with voids, or hot halo gas suppresses star formation gradually yet inexorably. Computational models also allow astronomers to test hypotheses about the universe's role in galactic death. By adjusting filament density, void proximity, or dark matter halo shape, models predict how environmental forces influence gas flows and star formation. Observed galaxies can then be compared to these predictions, validating the theory that cosmic starvation drives quenching in certain cases. The combination of simulation and observation transforms a snapshot of a galaxy into a dynamic understanding of its evolutionary trajectory. Advanced techniques in data processing and visualization make this research possible. Massive multi-wavelength datasets must be processed to remove noise, identify faint signals, and reconstruct three-dimensional structures. Machine learning algorithms detect patterns across thousands of galaxies, highlighting those that are dying. Visualization software converts raw data into detailed maps, showing star clusters, gas filaments, dust lanes, and velocity fields in a single coherent view. Scientists can then see the galaxy being killed, not as a single moment, but as a process unfolding across time and space. Integral field spectroscopy is another cutting-edge technique. Unlike traditional spectroscopy that captures a single spectrum, integral field units collect spectra across the entire face of a galaxy simultaneously. This allows astronomers to map velocity, chemical composition, and gas density across every region of the disk. For dying galaxies, integral field spectroscopy reveals regions where gas has been stripped, clusters where star formation continues in isolation, and zones where inflows from the cosmic web have ceased. The result is a detailed dynamic map showing not just the structure, but the functional death of the galaxy. Adaptive optics has expanded these capabilities from space-based telescopes to ground-based observatories. By correcting for atmospheric distortion, adaptive optics systems sharpen images, allowing the study of fine details in distant galaxies. Gas filaments, faint molecular clouds, and small star clusters become visible, enabling precise measurements of both structure and motion. In combination with spectroscopic mapping, adaptive optics provides an unprecedented look at the internal mechanics of dying galaxies. Time domain observations add yet another dimension. Repeated monitoring over months or years allows astronomers to detect subtle changes in brightness, star formation, or gas distribution. Outflows may accelerate, filaments may fragment further, and clusters may fade. Observing these changes in real time, even on the scale of human decades, provides insight into the dynamic processes that drive galactic quenching. Observatories with wide-field monitoring capabilities, like the Vera Rubin Observatory, enable these long-term studies. Simulations and observations are increasingly integrated. Multi-wavelength data inform initial conditions for models, while simulations predict structures that can then be verified observationally. For instance, a simulation may predict that gas stripped from the outer disk will create faint filaments detectable in radio wavelengths. Observers can then target these regions with ALMA or other radio arrays to confirm the model. This iterative process ensures that theoretical understanding aligns with empirical data, revealing the step-by-step mechanics of galactic death. Detecting dying galaxies also relies on coordinated surveys across wavelengths. Optical surveys identify potential candidates based on faint star clusters. Infrared and submillimeter observations confirm the absence or fragmentation of molecular clouds. X-ray mapping detects hot halos suppressing inflows. Spectroscopic measurements reveal disrupted velocities and stripped gas. By combining these datasets, astronomers construct a multi-dimensional view of the galaxy, showing not just that it is dying, but how the process unfolds across structure, gas, and motion. Cutting-edge imaging and computational techniques also allow scientists to trace galaxies within the cosmic web. Filaments and voids, invisible to the naked eye, become detectable through patterns in galaxy distribution, gas flows, and gravitational lensing. Observing a dying galaxy in context, its location relative to cosmic filaments, neighboring galaxies, and intergalactic gas explains why star formation has halted. It is not random. The universe orchestrates these outcomes. By combining all of these technologies, light detection, gas mapping, motion tracking, spectral mapping, simulations, adaptive optics, and time domain studies, astronomers can see a galaxy being killed. They witness depleted molecular clouds, faint or absent star clusters, disrupted inflows, hot gas preventing cooling, and structural remnants orbiting in quiet isolation. The Death Star galaxy is no longer just a faint spiral in the sky. It becomes a laboratory, a window into the complex interplay of cosmic forces that determine a galaxy's fate. Each technique contributes a piece of the puzzle. Optical imaging shows the aging stars. Infrared imaging traces hidden dust and cold regions. Radio and submillimeter arrays map molecular gas. X-ray observations detect energetic outflows. Spectral mapping measures velocities. Integral field units provide full spatial spectra. Simulations and computational models reconstruct the slow processes of quenching. Time domain studies track ongoing changes. Together, these tools transform invisible processes into observable phenomena, revealing galaxies dying in real time. The synergy of innovation, technology, and observation has turned a once invisible population of quenched galaxies into an accessible field of study. By combining precise instruments with sophisticated modeling, astronomers can detect faint signals, map motions, and trace the depletion of star-forming material. Galaxies once thought to be static objects become dynamic systems, their death visible in every photon, every gas filament, every spectral line. Even more remarkable is the ability to link observations of local dying galaxies to those in the distant universe. JWST and ALMA, with their unprecedented sensitivity, allow astronomers to detect galaxies at high redshift undergoing similar quenching processes. By comparing these distant galaxies with nearby examples like the Death Star galaxy, scientists can track the evolution of galactic death over billions of years, understanding how environment, cosmic web position, and internal depletion interact across cosmic time. Technologies like machine learning, spectral decomposition, and multidimensional simulations continue to push the boundaries. Faint outflows that were once undetectable are now measurable. Fragmented molecular clouds can be tracked across a galaxy's disk. Velocity fields reveal subtle stripping processes and disrupted inflows. Each advance sharpens the picture, allowing scientists not only to catalogue dying galaxies, but to understand the physical processes that end star formation. Observing a galaxy being killed has become a multisensory, multi-wavelength endeavor. Light, gas, and motion are all traced simultaneously. Structures invisible to optical telescopes emerge in radio or sub-millimeter wavelengths. Faint residual clusters are revealed in infrared. Hot gas halos glow in X-rays, while spectral lines trace the motion and composition of remaining clouds. Simulations translate these observations into dynamic narratives, showing how the galaxy transitions from life to quiescence across millions of years. The Death Star galaxy shows how these innovations converge. Its faint star clusters, fragmented gas, disrupted inflows, and hot surrounding halo are all detected through the combination of instruments and techniques. It is a galaxy being killed in plain sight, its demise observable across light, gas, and motion. These technologies allow astronomers to reconstruct every step, revealing the processes that slowly, inevitably, end star formation. How the Death Star galaxy challenges galaxy evolution models. The Death Star galaxy sits quietly in the cosmic darkness, but it is anything but ordinary. It challenges the rules astronomers thought they understood about how galaxies form, evolve, and die. For decades, models of galaxy evolution assumed a fairly predictable path. Gas inflows along cosmic filaments feed star formation, stars age, supernova recycle material, and galaxies slowly grow, occasionally colliding or merging but rarely stopping star formation completely unless extreme interactions occur. The Death Star galaxy refuses to follow that script. One of the first puzzles arises in its unexpected cessation of star formation. In most models, galaxies retain at least some gas over billions of years, especially spirals, which are fed by the cosmic web. But here is a galaxy structurally intact, yet with star formation almost entirely quenched. Its spiral arms, instead of glowing with blue, youthful stars, are dominated by older red stars. ALMA and JWST observations reveal that the cold gas needed for star formation has vanished or been fragmented into disconnected pockets. In simulations, such a depletion should require either violent collisions or rapid consumption through starbursts. But neither scenario fits the Death Star galaxy. It's alive structurally but functionally dead. The cosmic web, the network of filaments and voids spanning the universe, plays a central role in feeding galaxies. Models had assumed that spiral galaxies connected to multiple filaments maintain a steady inflow of gas over billions of years, allowing star formation to continue almost indefinitely unless a major external event occurs. Yet the Death Star galaxy appears to have been cut off without any obvious catastrophic collision. Its quenching seems driven by environmental factors invisible to older models: subtle misalignment with cosmic filaments, isolation within a local void, and the slow heating of surrounding gas. These processes were largely overlooked in traditional galaxy evolution simulations, which treated filaments as persistent and uniform. Dark matter halos are another challenge. Conventional models suggest that the mass of a galaxy's dark matter halo regulates gas retention and cooling. Larger halos should retain gas and allow continuous star formation, while smaller halos are more susceptible to quenching. The Death Star galaxy seems to defy this principle. Observations indicate that it resides in a reasonably massive halo, yet it has lost its cold gas. Hot gas halos detected in X-ray light show that residual material is being prevented from cooling and forming stars, indicating that halo mass alone cannot explain quenching. This forces theorists to reconsider the balance between dark matter, gas cooling, and environmental pressures. The galaxy's high-energy outflows also raise questions. Observations show faint but persistent winds of ionized gas leaving the disk, stripping remaining material. Simulations had predicted that such outflows would require extreme events like active galactic nuclei or rapid starbursts. The Death Star galaxy, however, shows these winds without such extreme activity. The result is a subtle, ongoing depletion of star-forming material that occurs over millions of years, defying simple cause and effect expectations in classical models. Even the morphology of the galaxy challenges assumptions. Spiral galaxies are generally thought to be resilient, maintaining structure while slowly forming stars. Yet here is a spiral, clearly organized, with arms and a central bulge intact, but its functionality halted. The Death Star galaxy demonstrates that morphology does not necessarily indicate vitality. In other words, appearance alone cannot be used to infer a galaxy's evolutionary state, a warning for astronomers relying solely on optical imaging without multi-wavelength analysis. This galaxy also pushes the limits of understanding cosmic web dynamics. Filaments are expected to act like cosmic rivers, channeling gas from the intergalactic medium into galaxies. Yet the Death Star galaxy seems partially disconnected from these rivers, starved despite structural integrity. Observations from the Vera Rubin Observatory and other large surveys reveal that the surrounding environment, local voids, neighboring galaxies, and filament density plays a decisive role. The galaxy's isolation has reduced inflows to the point where star formation cannot be sustained. Traditional models did not account for the subtle but cumulative impact of filament misalignment and void-induced isolation, making this galaxy a key test case for updating our understanding. Spectral mapping and kinematic studies further challenge models. Residual gas moves in fragmented patterns, velocities inconsistent with predictions based on gravity alone. ALMA and JWST spectra show molecular clouds that are misaligned, disrupted, or slowly being stripped by low-level outflows. Existing galaxy evolution simulations predicted that gas in a stable spiral should either settle into the disk or be expelled in dramatic events. The Death Star galaxy demonstrates that gas depletion can occur gradually, in faint, fragmented motions invisible without high-resolution spectroscopy, forcing theorists to incorporate subtle dynamical processes into their models. The implications for star formation quenching are profound. Prior models emphasized violent events, mergers, starbursts, or active galactic nuclei as the primary quenching mechanisms. The Death Star galaxy shows that slow, subtle processes can suffice: disconnection from the cosmic web, gradual heating of gas halos, low-level stripping, and fragmentation of molecular clouds. Star formation can end quietly, without dramatic fireworks, leaving a structurally intact but functionally dead system. This requires a recalibration of how models predict galaxy populations at different cosmic epochs, particularly when assessing how many galaxies survive as star-forming versus quiescent systems. Even chemical composition challenges expectations. Observations show that elements generated by previous star formation remain trapped in the galaxy, yet new star formation fails to recycle them into new clusters. This contradicts models that assumed chemical enrichment alone would trigger ongoing star formation, highlighting the role of environmental suppression over internal processes. The galaxy's quenching is therefore not just about fuel depletion. It's about the universe's ability to isolate and regulate galaxies at large scales. The Death Star galaxy also questions the universality of timescales in galaxy evolution. Models typically assign approximate lifespans for star formation in spirals, with gradual decline over billions of years. Yet, the galaxy's star formation appears to have slowed far earlier than its size, mass, or halo would predict. Its quenching timeline cannot be explained by internal exhaustion alone. Environmental and cosmic web factors must be invoked. This forces theorists to reconsider how timescales are applied across different environments, including dense clusters, filaments, and voids. Another challenge is multiscale interaction. The galaxy demonstrates that quenching is not purely internal or external, it is a combination. Gas heating, halo dynamics, filament disconnection, dark matter interactions, and faint outflows all act together. Traditional models often separate internal and external quenching, but the Death Star galaxy shows that subtle interplay across scales drives the process. Simulations now attempt to incorporate these layered interactions, but the complexity revealed by this galaxy exceeds previous predictive power. Observations also have consequences for understanding galaxy populations over cosmic time. The Death Star galaxy suggests that a larger fraction of galaxies may enter slow quenching phases than previously recognized. Surveys reveal other galaxies with similar faint fragmented molecular gas, low star formation, and isolated positions in the cosmic web. This indicates that our census of red and dead galaxies may underestimate the number of galaxies dying quietly, requiring a reassessment of galaxy population statistics and evolutionary pathways. The galaxy's characteristics have forced updates in simulation models. Computational models now include detailed tracking of filament connectivity, hot gas halo dynamics, low-level outflows, and kinematic fragmentation. They simulate the gradual removal of star-forming fuel over hundreds of millions of years, capturing the faint, almost invisible processes that terminate star formation. Without the Death Star galaxy as a reference, these refinements may never have been prioritized, showing how a single extreme system can recalibrate theoretical understanding. Even observational strategies are being rewritten. Multi-wavelength campaigns are now designed to detect subtle quenching signatures, fragmented molecular clouds, faint X-ray halos, misaligned inflows, and velocity irregularities. Galaxies once assumed to be active spirals may now be reclassified based on subtle spectral and kinematic evidence. The Death Star galaxy serves as the template for identifying other systems in transition, highlighting the need for integrated, multi-observatory and high-resolution studies. The Death Star galaxy forces us to think differently about galaxy evolution, cosmic web dynamics, and star formation quenching. It demonstrates that galaxies are not simply fuel-dependent engines, but dynamic systems embedded in a complex cosmic environment. In these environments, isolation, filament connectivity, halo heating, and subtle stripping processes determine whether a galaxy continues to shine or fades quietly. Traditional models focused on catastrophic events or simple inflow-outflow balances must now accommodate slow, cumulative, and subtle mechanisms capable of terminating star formation without structural destruction. Spectroscopic and imaging innovations reveal the delicate interplay of motion, composition, and energy that drives quenching. Simulations calibrated with these observations reproduce subtle stripping, misaligned inflows, and hot halo suppression. Multi-wavelength studies reveal the multi-component nature of quenching, showing that star formation depends not just on internal fuel, but on the galaxy's relationship with the cosmic web and intergalactic environment. The Death Star galaxy, through its extreme but observable properties, redefines the limits of what is possible in galactic evolution and challenges astronomers to rethink long-held assumptions about life, death, and survival in the universe. Dark matter and intergalactic forces. The Death Star galaxy is not only unusual because it has stopped forming stars, but because it forces astronomers to rethink how galaxies interact with the universe around them. For decades, galaxies were often treated as self-contained systems. Gas forms, stars evolve, and gravity keeps everything in place. Dark matter was considered a stabilizing scaffold, providing the mass needed to hold galaxies together. The intergalactic medium, the vast, thin gas between galaxies, was mostly ignored in models, except during dramatic collisions or mergers. The Death Star galaxy challenges all of that. Dark matter is invisible, but its influence is everywhere. Galaxies form within massive dark matter halos, and these halos are thought to regulate gas inflow and star formation. Denser halos hold on to cold gas, preventing it from escaping, while smaller halos allow gas to flow out more easily. The Death Star galaxy resides in a halo massive enough that conventional models predict it should retain a healthy supply of star-forming gas. Yet observations reveal a nearly empty gas disk, a quiescent stellar population, and faint residual molecular clouds. This mismatch raises questions about the role of dark matter beyond simple gravitational binding. The Death Star galaxy suggests that halo mass alone cannot protect a galaxy from cosmic processes. It appears that even galaxies embedded in substantial dark matter scaffolds can lose their gas, slow star formation, and eventually die if environmental conditions interfere with gas replenishment. The intergalactic medium plays a central role in this process. The space between galaxies is not empty. It contains tenuous gas, both hot and cold, and this medium interacts with galaxies in ways that were previously underestimated. Filaments of the cosmic web channel gas toward galaxies, feeding star formation, while voids can isolate galaxies, cutting off inflows. Observations of the Death Star galaxy show that it sits near a low-density region, where gas inflows from filaments are weak or misaligned. This isolation has starved the galaxy of the raw materials needed to sustain new stars. High-energy outflows detected in X-ray and radio wavelengths add another layer. The Death Star galaxy shows faint streams of gas being expelled from its disk. These outflows are not caused by supernova explosions or active galactic nuclei alone. They appear to result from subtle interactions between the galaxy's halo, dark matter, and surrounding intergalactic gas. Hot halo gas may prevent residual cold gas from cooling, while tidal forces from cosmic filaments tug at remaining gas, slowly removing it from star-forming regions. These processes demonstrate that galaxies are not protected simply by their mass or dark matter content. The universe itself can strip away what sustains them. The Death Star galaxy also challenges the assumption that quenching requires violent events. Classical models emphasized collisions, mergers, and bursts of star formation as the main ways to shut down a galaxy. Here, quenching is gradual. Multi-wavelength observations show slow depletion of molecular clouds, misaligned gas inflows, and disrupted kinematics. Computational models now incorporate subtle forces from the intergalactic medium and interactions with the cosmic web, showing that a galaxy can be slowly killed without catastrophic events. This realization has implications for dark matter theories. Halo mass is no longer sufficient to predict star formation activity. Instead, the interaction between dark matter, gas halos, and the intergalactic medium must be considered. For example, a galaxy may sit in a dense dark matter halo but be cut off from gas inflows by its position in a void. Alternatively, filament misalignment may redirect inflows away from the disk, leaving a galaxy structurally intact but star-forming dead. The Death Star galaxy shows that dark matter's role is more complex than just providing gravity. It is part of a dynamic system interacting with cosmic filaments and voids. Spectral mapping and simulations reveal how these interactions operate over time. Molecular clouds that once fed star formation now drift in fragmented motions. Residual gas heats up in the halo, preventing cooling. Weak outflows slowly remove material. In simulations, a galaxy like the Death Star loses its ability to form stars over hundreds of millions of years, tracing a silent, invisible death. Observing this in real galaxies confirms that dark matter and the intergalactic medium act together in ways not captured in older models. The Death Star galaxy also demonstrates the vulnerability of galaxies within the cosmic web. Filaments, voids, and clusters are not just background structures. They actively shape a galaxy's evolution. Gas inflows along filaments fuel stars, while voids can isolate galaxies and prevent replenishment. Observations show that even small deviations from ideal filament connections can starve a galaxy, while simulations reproduce the same effect. The Death Star galaxy is an extreme example, highlighting the sensitivity of star formation to environmental factors. Radio and submillimeter observations of molecular gas confirm that remaining clouds are isolated and unable to feed the disk. These observations show that gas depletion is not uniform. Some regions may retain cold clouds, but they are disconnected from areas that can sustain new stars. The intergalactic medium and dark matter halo influence the location and movement of these clouds, showing that galaxies cannot survive without external connections. X-ray observations reveal hot halos surrounding the galaxy, further preventing star formation. Heated by cosmic processes or trapped energy from prior star formation, this gas forms a barrier between the galaxy and potential inflows from the intergalactic medium. Even if filaments deliver gas, it cannot cool fast enough to collapse into new stars. Dark matter alone cannot reverse this effect. Only understanding the interaction between halo, intergalactic gas, and cosmic filaments can explain the galaxy's death. Multi-wavelength studies combine optical imaging, infrared observations, radio mapping, and X-ray detection to capture the full picture. Optical imaging shows faint aging stars. Infrared reveals sparse molecular clouds. Radio mapping tracks the depletion of hydrogen filaments. X-rays highlight hot halo gas and faint outflows. The Death Star galaxy is not dying in isolation. It is being actively shaped and controlled by forces beyond its disk. Simulations and computational models are now essential. Using input from multi-wavelength observations, models reproduce the slow quenching process, showing how filament misalignment, void isolation, halo heating, and weak outflows interact. Dark matter is part of this system, influencing the distribution of gas and the efficiency of stripping, but it cannot prevent environmental forces from gradually killing the galaxy. The Death Star galaxy is also helping to rethink galactic life cycles. Quenching can happen without collisions, mergers, or active nuclei. A galaxy can appear healthy, with spiral structure and a massive halo, yet still be losing its ability to form stars. Multi-wavelength observations show the delicate balance between internal structure, halo support, and environmental influence. The universe itself, its filaments, voids, and intergalactic medium, is capable of shutting down a galaxy quietly over millions of years. This challenges long-held assumptions that galaxies are largely autonomous. The Death Star galaxy shows that no matter how massive or structurally sound a galaxy is, it is vulnerable to the universe around it. Cosmic starvation, environmental isolation, halo heating, and faint outflows act together to terminate star formation. Multi-wavelength studies capture this process in action, revealing galaxies as dynamic systems interacting continuously with the cosmic web. The galaxy's subtle outflows, hot gas halos, and fragmented molecular clouds provide direct evidence that intergalactic medium interactions are a dominant factor in quenching. Dark matter halos, while essential for gravitational structure, cannot prevent a galaxy from being starved. The Death Star galaxy shows that galaxies are part of a larger network, dependent on gas flows along filaments and vulnerable to isolation in voids. Spectral mapping, simulations, and computational models reveal how this vulnerability operates across time. Gas that once fueled stars drifts or evaporates. Halo heating traps residual material. Inflows from filaments become weak or misaligned. Velocity mapping shows disrupted motions. Every observation points to the same message. Galaxies are not self-sufficient. They are embedded in a dynamic universe, susceptible to forces acting across millions of light-years. The Death Star galaxy is an extreme example, but it represents a broader phenomenon. Multi-wavelength surveys and high-resolution simulations reveal other galaxies in similar situations, demonstrating that cosmic starvation is not rare. The interplay of dark matter, intergalactic medium, cosmic filaments, and voids shapes galactic evolution. Star formation is not guaranteed by internal fuel alone. It requires continued access to cosmic resources. Observatories like Hubble, JWST, ALMA, and Vera Rubin are critical in detecting these interactions. Optical light shows the aging stellar population. Infrared reveals sparse molecular clouds. Radio traces hydrogen depletion. X-ray highlights hot gas. Spectral mapping measures motion, and simulations predict the long-term evolution. Together, these tools allow astronomers to see galaxies being starved by the universe itself. The Death Star galaxy serves as a stark reminder that galaxies are not isolated islands. They exist within the cosmic web, reliant on inflows and vulnerable to environmental disruption. Multi-wavelength observations and simulations show how subtle forces, filament misalignment, void isolation, halo heating, and faint outflows can kill star formation quietly over millions of years. Even dark matter, once thought to provide immunity against environmental factors, cannot fully protect galaxies. The Death Star galaxy demonstrates that star formation depends not only on internal mass or structure, but on the galaxy's connection to the universe itself. Observations and models now show that the life and death of galaxies are intimately tied to cosmic-scale forces, revealing a new level of vulnerability and interdependence in the universe. Simulations of the Death Star galaxy. Simulations allow us to see the Death Star galaxy in motion across billions of years, revealing the slow unraveling of star formation in ways impossible to observe directly. The galaxy's star-forming regions dim, with blue clusters gradually fading into red as the gas that once fueled them disappears. At the start, the Death Star galaxy appears robust. Spiral arms are filled with dense molecular clouds. Bright clusters form along the disk, and the halo holds streams of cold gas ready to replenish star-forming regions. Light pours from the youngest stars, illuminating the structure with vibrant energy. The galaxy seems alive, thriving, its rotation steady, its spiral arms tightly wound. Over the first few 100 million years, subtle changes begin. Simulated gas inflows from the cosmic web, slow, misaligned filaments fail to deliver the fuel needed to sustain new star formation. Molecular clouds in the outer arms fragment and drift apart. The simulation shows clouds thinning, collapsing less efficiently, their internal densities too low to ignite new stars. Watch as the outer spiral arms lose their brightness, faint streaks replacing vivid clusters. Star formation begins a gradual decline. Meanwhile, the galaxy's halo interacts with the intergalactic medium. Hot gas accumulates, surrounding the disk like a faint glowing cage. Streams of cooler gas that would normally sink into the disk now struggle to penetrate the halo, heating as they move through. The simulation visualizes this heating in soft, translucent layers overlaying the galaxy's structure. Outflows, faint but persistent, remove leftover molecular clouds from the central regions. Gas that could have formed new stars is swept away slowly, like embers carried off by a cosmic wind. By 1 billion years into the simulation, the Death Star galaxy is visibly dimmer. Spiral arms are still intact, but the brightest clusters have vanished. Star-forming regions in the outer disk flicker intermittently, failing to sustain the bursts of light seen earlier. Residual clouds drift in irregular patterns, traced in the simulation as thin, wavering threads of gas. The halo dominates visually, an X-ray glow representing trapped hot material. The galaxy rotates, but its vitality is fading, visible in the gradual decline of luminosity across the disk. Spectral mapping in the simulation adds another layer of drama. Blue wavelengths, once prominent in star-forming regions, fade steadily. Infrared emissions from dust are sporadic, indicating fragmented molecular clouds unable to sustain new stars. Radio signals trace hydrogen filaments thinning over time, while X-ray outputs show the hot halo suppressing further inflows. The simulation allows the viewer to follow every component – stars, gas, dust, and halo, losing energy, one by one, until the galaxy appears starved and passive. Small-scale interactions are revealed in incredible detail. Some molecular clouds survive longer than others, clumping near the galaxy's center, while outer regions lose material entirely. The simulation visualizes this with cinematic clarity. Inner clusters glow faintly, while the outer disk fades to near invisibility. Gas motion is disrupted. Inflows once aligned with spiral arms become misdirected, and faint outflows strip material along the disk edges. Every change is subtle, imperceptible over human timescales, yet transformative over billions of years. 2 billion years in, the galaxy's star formation is mostly halted. The disk is a muted red, illuminated only by aging stars. Spiral arms remain visually distinct, but almost entirely devoid of new clusters. The simulation highlights this dimming. Watch as each arm loses its blue glow, the edges flickering as residual gas dissipates. Clouds that could have ignited are either heated in the halo or stripped by faint outflows. The rotation continues, but the galaxy's energy is fading, leaving a quieter, older population behind. Dark matter halos are animated in the simulation to show their role in structure retention. The Death Star galaxy remains intact, held together by its invisible scaffolding. Gravity preserves the spiral arms, maintains the disk, and stabilizes residual clouds. Yet dark matter cannot replenish lost gas or reignite star formation. The cinematic effect is striking. The galaxy is alive in form, but slowly dying in function. A skeletal spiral, slowly losing its vibrancy. By 3 billion years, the Death Star galaxy is nearly dormant. The simulation tracks every remaining cloud, visualizing tiny pockets of potential star formation flickering briefly before fading. Hot halo gas dominates, glowing faintly in X-ray wavelengths, preventing material from cooling. The disk rotates like a clockwork mechanism, its structure pristine, yet no new stars emerge. The simulation allows viewers to watch this process in real time, gas and light declining in a silent ballet of cosmic starvation. Filament misalignment is highlighted dramatically in the simulation. Streams of intergalactic gas that once fed the galaxy now bypass the disk entirely. Gas that would have traveled along filaments dissipates in the surrounding medium or is trapped in the halo. The Death Star galaxy, despite being massive and structurally intact, is cut off from its lifeline. The cinematic narrative shows filaments fading, streams thinning, and the galaxy slowly going dark, a visual testament to environmental vulnerability. By 4 billion years, the simulation portrays the galaxy as a ghost of its former self. Residual star clusters in the central bulge glow faintly, isolated and aging. Spiral arms rotate gracefully, yet they are devoid of new stars. Molecular clouds are sparse and fragmented, shown as delicate wisps drifting in the simulation, unable to coalesce into stellar nurseries. Hot gas halos continue to suppress inflows, and faint outflows carry away the last remnants of material. The viewer can follow every process simultaneously, watching the death of star formation unfold layer by layer. Spectral decomposition in the simulation allows every wavelength to tell its story. Optical emissions show fading clusters. Infrared highlights faint isolated clouds. Radio maps reveal thinning hydrogen filaments. X-ray visuals depict hot halo gas. By layering these components, the simulation conveys the galaxy's decline in cinematic detail. One by one, the star-forming regions dim, gas filaments vanish, and the galaxy moves toward a quiescent state. By 5 billion years, the Death Star galaxy has entered a near-final stage of quiescence. The disk is dominated by older stars, faintly glowing red. Spiral arms rotate slowly, ghost-like in appearance. Molecular clouds are nearly gone, and inflows from cosmic filaments are negligible. Even residual outflows are faint, leaving only subtle motions in the halo. Simulations animate this decline gradually, showing every small shift, fragment, and loss in vivid cinematic clarity. By 6 billion years, the galaxy is effectively dead. Star formation is negligible, molecular clouds are almost non-existent, and the halo dominates the remaining structure. Filaments have disappeared from view in the simulation, leaving the galaxy isolated. The spiral arms, still intact in rotation, glow only with aging stars. The cinematic effect is haunting. Watch as every once vibrant cluster has dimmed, every gas filament has dissipated, and the galaxy drifts silently through the cosmic web. The simulation also allows viewers to explore the process from multiple perspectives. Zooming into the central bulge, faint clusters flicker and fade. Rotating above the disk, spiral arms are seen losing their gas and light progressively. Pulling back to a wider cosmic view, the galaxy's isolation within the filament network is highlighted, showing how inflows cease and environmental starvation dominates. This multi-scale cinematic perspective captures the full drama of galactic death over billions of years. Dark matter halos remain as silent observers. They preserve the galaxy's structure, holding the disk and spiral arms in place, but cannot restore vitality. Gas, stars, and outflows continue their slow, inexorable decline, emphasizing the limits of gravity in reversing cosmic starvation. The simulation allows these invisible processes to be visualized dynamically, showing the interplay of structure, gas motion, and environmental isolation. By 7 billion years, only the faintest hints of former activity remain. Star-forming regions have vanished, molecular clouds are scattered fragments, and the hot halo dominates. The cinematic effect is complete. Watch as the galaxy transitions from a vibrant spiral to a quiet red quiescent system, a Death Star in its own right, slowly dimming under the influence of cosmic forces over billions of years. The simulation emphasizes gradualism. There is no dramatic explosion, no sudden collapse. Instead, every pixel of gas, dust, and star is animated in a slow, cinematic procession. Residual star clusters flicker and fade. Gas streams weaken, fragment, and dissipate. Outflows remove material silently. Spiral arms rotate gracefully, yet the energy of youth is gone. This visual storytelling allows the Death Star galaxy to be seen not as a static object, but as a dynamic system, dying over vast cosmic timescales. Integral field spectroscopy is simulated simultaneously, showing velocities of gas and stars in 3 dimensions. Misaligned inflows, disrupted motions, and faint outflows are all captured. Viewers can see the molecular clouds failing to collapse, rotating disks losing coherence, and halo gas suppressing star formation. The cinematic visualization transforms billions of years of slow quenching into a visual, almost tangible narrative. Even faint pockets of star formation are temporary. The simulation shows clusters that survive briefly before fading. illustrating how environmental factors gradually extinguish stellar birth. Residual gas heats up, disperses, or is stripped, emphasizing that the galaxy is dying not from a single event, but from a complex, continuous interplay of cosmic forces. Simulations like this allow astronomers and viewers alike to witness the slow death of a galaxy in unprecedented detail. Each component, stars, gas, halo, filaments, is animated dynamically, showing the gradual, almost imperceptible processes that extinguish star formation. The Death Star galaxy is transformed from a distant, faint object into a vivid, cinematic laboratory for understanding how galaxies end their life cycles. Models and observations of the Death Star galaxy. The Death Star galaxy is not only an unusual target for astronomers, it is also a testing ground for the models that try to explain how galaxies evolve. Simulations allow scientists to track the behavior of gas, stars, dark matter, and cosmic filaments over billions of years, while observations capture snapshots of these processes in real time. The intersection of models and observations transforms the galaxy from a distant, static object into a dynamic system, revealing how theory and evidence can align, or sometimes challenge each other. At first glance, models predicted that a galaxy with the Death Star's mass, structure, and halo size should remain actively forming stars. Spiral arms would maintain molecular clouds, dark matter would stabilize the disk, and inflows along filaments would provide a steady supply of gas. Yet observations, particularly from ALMA, JWST, and Hubble, revealed something very different. A galaxy structurally intact, but largely star-forming dead. This mismatch sparked intense efforts to adjust models to fit reality. In the models, gas inflows gradually weaken as the galaxy drifts toward low-density regions of the cosmic web. The simulation animates filament misalignment, showing streams of gas bypassing the galaxy's disk. Observations support this. Radio mapping and spectral measurements confirm that gas inflows are minimal, and molecular clouds in the outer arms are sparse or fragmented. Watch as simulations and observations converge, the outer spiral arms dimming as predicted, each star-forming region fading one by one. Simulations of the galaxy's halo and dark matter are also strikingly consistent with observations. The model predicts a hot gas halo surrounding the disk, preventing remaining gas from cooling efficiently. X-ray observations reveal exactly this phenomenon. Faint, diffuse hot gas extending beyond the visible disk. Molecular clouds are trapped, unable to collapse into new stars. The simulation shows residual clouds drifting in misaligned motions, while outflows carry small amounts of material away. Observations confirm these motions, captured in spectral mapping and radio studies, showing how models accurately recreate the complex interplay of halo, gas, and stellar structures. One of the most cinematic aspects of the simulation is the gradual fading of star-forming regions. Inner clusters, initially bright and dense, lose gas slowly. The simulation animates this process across billions of years. Watch as the galaxy's star-forming regions dim, one by one. Observations match this pattern. Optical imaging from Hubble shows older stellar populations dominating the disk. Infrared data reveals sparse pockets of molecular clouds, indicating that even the densest regions cannot sustain new star formation. The simulation does not just predict these trends, it visually mirrors them, allowing scientists to confirm that models capture real processes. Filamentary connections are another area where models and observations align. The simulation traces inflows along cosmic filaments, showing how misalignment and void-induced isolation reduce gas delivery to the galaxy. Observations support this. Surveys from the Vera Rubin Observatory show a lack of dense filaments near the galaxy, confirming that it is partially cut off from its cosmic lifeline. By animating the gradual disconnection from the cosmic web, the simulation captures a dynamic that was difficult to detect before multi-wavelength surveys, turning abstract theory into visually verifiable events. Outflows and gas stripping are represented with cinematic clarity in the simulations. faint ionized streams peel away from the disk over millions of years. Models predicted these outflows would be subtle yet persistent, removing residual star-forming material. Observations confirm this in X-ray and radio wavelengths. Spectral mapping shows gas velocities and directions consistent with modeled predictions. The simulation allows viewers to watch the slow depletion in real time, while observations provide tangible evidence that the galaxy's quenching follows the same path. Temperature evolution in the simulation also matches measured data. The galaxy's hot halo prevents cooling, while remaining gas clouds heat up as they drift. X-ray observations capture this hot material, providing a direct comparison with models. Residual molecular clouds are isolated and unstable, unable to form stars efficiently. The simulation visualizes this with glowing halos and drifting gas threads, while observational data confirms these features in reality. The match between predicted gas temperatures and observed X-ray signatures underscores the accuracy of current models in capturing environmental quenching mechanisms. Simulated chemical abundances also align with observations. Models predict that elements from past star formation remain in place but are not recycled efficiently into new stars. Observations reveal the same pattern. The galaxy retains metals in older stars, but the lack of cold gas prevents the creation of new clusters. The simulation animates these distributions across the disk, showing aging stars glowing in red, while molecular gas remains sparse and misaligned. Observational data confirm these spatial patterns, providing another layer of agreement between models and reality. Velocity patterns in the simulation reflect disrupted gas dynamics. Clouds that survive are fragmented, moving in misaligned orbits that prevent collapse. Observations confirm these irregular motions through spectral measurements, showing a remarkable match between predicted kinematics and reality. Watch as simulated clouds twist, drift, and fade across the disk, mimicking the real velocities measured in the galaxy. The alignment between theoretical motion and observed kinematics provides strong evidence that models now capture the subtle processes driving the galaxy's death. Simulations also explore the timeline of quenching. The Death Star galaxy's star formation declines gradually over billions of years, with outer arms dimming first and inner regions following later. Observations match this pattern. Optical and infrared imaging show that outer spiral arms are devoid of bright blue clusters, while the central bulge retains faint red stars. The simulation animates this chronological fading, allowing viewers to see star-forming regions vanish sequentially, mirroring what telescopes reveal across different wavelengths. Residual gas structures are also reproduced in models. Small pockets of molecular clouds survive longer in the simulation, concentrated near the galaxy's center, while outer regions become increasingly devoid of material. Observations confirm these pockets, showing faint infrared emission from isolated clouds. The match between predicted gas survival and real data demonstrates that models now capture the uneven, spatially dependent process of galaxy quenching. Dark matter halos in the simulation stabilize structure, preventing the galaxy from collapsing while star formation declines. Observations show the spiral arms remain intact, consistent with model predictions. The cinematic effect is striking. The galaxy rotates gracefully, its structure preserved, yet star formation vanishes. This alignment between simulated and observed morphology reinforces the accuracy of models in capturing both dynamic motion and structural stability during quenching. Filamentary feeding is another feature captured well in simulations. Streams of gas that once sustained star formation are redirected or blocked, leading to starvation. Observations confirm that nearby filaments are sparse or misaligned, depriving the galaxy of inflows. In the simulation, this disconnection is animated with streaming gas fading as it bypasses the disk. Optical, radio, and infrared observations show consistent results. Gas that could fuel new stars is absent or fragmented. The agreement is remarkable, showing models can now replicate the interaction between galaxies and their cosmic environment. Temperature, density, and kinematic evolution all converge in these simulations. Hot halo gas prevents cooling. Residual clouds are misaligned. Filaments are weak or absent. Faint outflows remove material. Observations across multiple wavelengths detect all these features. The match between predicted and measured properties confirms that models capture the mechanisms driving quenching, a combination of environmental starvation, halo heating, and subtle gas removal. Simulations also reveal the role of time. Quenching is not instantaneous. It occurs over billions of years, with fading star-forming regions, isolated molecular clouds, and slowly dimming clusters. Observations show a snapshot of this gradual process, but the simulation allows it to be visualized as a continuous cinematic narrative. Watch each spiral arm lose its blue clusters, see molecular clouds drift and fragment, and observe faint halo gas suppressing inflows. Theory and observation align to show a galaxy dying quietly, yet dramatically, under the universe's influence. By combining simulations with multi-wavelength observations, astronomers can now trace the full life cycle of the Death Star galaxy's star-forming decline. Optical images show aging stars, infrared detects sparse clouds, radio maps reveal thinning hydrogen filaments, and X-rays highlight hot halo gas. The simulation animates all of these components together, showing them dim and dissipate sequentially. Observations confirm that every aspect of the galaxy's decline, spatial, temporal, and kinematic, matches theoretical predictions. Simulated spectra reveal gas motion, inflow direction, and velocity dispersion. Observational data shows the same irregular, fragmented velocities. Faint outflows predicted in models appear in X-ray and radio measurements. Temperature gradients, halo heating, filament disconnection, and cloud fragmentation all align. The Death Star galaxy becomes a cinematic example of how simulations and reality intersect, allowing astronomers to see the processes of quenching play out over billions of years. This synergy between models and observations is transforming our understanding. Simulations predict subtle processes that were previously invisible: gradual disconnection from the cosmic web, faint outflows, halo heating, and misaligned gas clouds. Observations now confirm each element, demonstrating that the Death Star galaxy is not an anomaly, but a laboratory for testing theories of galaxy evolution and environmental quenching. Spectral, kinematic, and multi-wavelength mapping ensures that models are not just abstract predictions. They are cinematic visualizations of a galaxy dying over time. Watch as star-forming regions dim, molecular clouds fragment, inflows misalign, and outflows carry away residual gas. Every detail predicted in the simulation finds its counterpart in observations, confirming that models now capture the subtle and dramatic processes shaping the galaxy's death. Speculative frontiers. Could this happen to our galaxy? The Death Star galaxy shows how a galaxy can stop forming stars and gradually die. Looking at it raises the question, could the Milky Way face a similar fate? At first glance, the Milky Way seems different. It is rich in gas, actively forming stars, and sits within a network of cosmic filaments that continuously deliver fresh material. Its spiral arms are vibrant, molecular clouds abundant, and its halo contains enough dark matter and hot gas to stabilize the disk. Star formation continues steadily, unlike the Death Star galaxy, where cold gas is depleted and outflows remove material. Despite these differences, the Milky Way is not immune to the same processes that killed the Death Star galaxy. One condition is the supply of gas from the cosmic web. If the galaxy were to drift into a region with fewer filaments or weaker connections, inflows of gas would decrease. Without a steady supply of cold hydrogen, molecular clouds could no longer collapse into new stars, and star formation would slow. While this is unlikely in the short term, over billions of years, the Milky Way could experience environmental starvation similar to what happened to the Death Star galaxy. Galactic collisions are another factor that could affect the Milky Way. The most notable example is the future collision with the Andromeda galaxy. Current predictions place this event in roughly 4 billion years. Such a collision could compress gas and trigger bursts of star formation temporarily. At the same time, tidal forces from the merger could remove or redistribute gas, potentially leaving the combined galaxy with fewer regions capable of forming new stars over the long term. Smaller interactions with satellite galaxies could also strip molecular clouds from the disk or provide additional fuel depending on the dynamics. The Milky Way's halo plays a critical role in its stability and star formation. The hot gas within the halo maintains pressure around the disk and helps prevent structural collapse. However, if the halo were to heat further due to black hole activity or external influences, cold gas might be trapped and unable to feed star formation. Without gas cooling efficiently, star-forming regions would gradually fade. While the halo currently supports ongoing star formation, changes in temperature or pressure over billions of years could alter this balance, increasing the risk of slow quenching. The intergalactic medium surrounding the Milky Way also affects its star formation potential. Gas densities in neighboring filaments may shift due to large-scale cosmic flows. If the galaxy's environment changes and inflows weaken, the Milky Way could face conditions similar to those of the Death Star galaxy. Over time, insufficient gas supply would reduce the formation of new molecular clouds, slowly decreasing star formation. While this scenario is rare, it demonstrates how environmental factors beyond the galaxy itself can have a decisive impact. Mergers with satellite galaxies provide both opportunities and threats. On one hand, gas-rich satellites could supply new material and prolong star formation. On the other hand, tidal interactions can strip gas from the Milky Way, removing fuel for star formation. The balance between these processes is delicate, and small changes in the timing or mass of incoming satellites could determine whether the galaxy continues forming stars or begins to decline. High-energy phenomena such as black hole activity also influence the galaxy's evolution. Sagittarius A*, the Milky Way's central black hole, is currently quiet. If it were to become active in the future, energy released could heat gas in the disk or halo. Heated gas would be less likely to collapse into new stars, reducing star formation rates. Combined with environmental changes, such as reduced gas inflow or tidal stripping, this could slowly starve the galaxy. While the Milky Way is massive and well-connected, the Death Star galaxy demonstrates that even large galaxies can experience quenching if conditions align. Isolation from inflows, halo heating, outflows, and depletion of molecular gas can lead to a galaxy structurally intact but incapable of forming new stars. The Milky Way, while currently active, could theoretically face similar pressures if its environment changes, or if internal processes such as black hole activity and halo heating increase. The rarity of galaxies like the Death Star is notable. Most spiral galaxies maintain gas inflows, continue forming stars, or experience periodic interactions that rejuvenate star formation. Death Star-like quenching is uncommon, but models suggest that any galaxy, including the Milky Way, could experience it under the right combination of cosmic forces. The Milky Way's size and connectivity reduce the likelihood in the near term, but over cosmic timescales, slow quenching remains a plausible outcome. Future collisions beyond Andromeda could also influence the Milky Way's fate. Encounters with other galaxies, large or small, can alter gas distribution, trigger starbursts, or remove fuel entirely. Tidal forces during mergers redistribute gas and stars, sometimes preventing the formation of new clusters. Environmental factors combined with mergers could eventually reduce the Milky Way's star formation efficiency, mirroring the processes observed in the Death Star galaxy. Cosmic flows and filamentary connections remain central to sustaining star formation. The Milky Way relies on filaments for a continuous supply of gas. If these connections weaken or change, gas delivery could slow, leading to gradual starvation. This emphasizes that galaxies are not isolated. They exist within a larger cosmic network, and changes in that network can directly impact star formation and overall galaxy evolution. Dark matter halos stabilize galaxy structure but do not replace gas or enable new star formation. While the Milky Way's halo preserves the disk, spiral arms, and bulge, It cannot prevent quenching if the galaxy loses access to cold gas. The Death Star galaxy shows that structural integrity can remain even as star formation ceases, a scenario the Milky Way could face under extreme cosmic circumstances. Environmental isolation is another factor. The Milky Way currently resides in a moderately dense region of the local group. If it were to drift toward a lower density region, gas inflows from cosmic filaments could decrease, reducing the formation of new stars. While the Milky Way's trajectory is relatively stable, small shifts in the distribution of matter across cosmic scales could alter inflow patterns over billions of years, creating conditions favorable for slow quenching. Interactions with satellite galaxies and high-velocity clouds further complicate the picture. Some satellites could supply gas, prolonging star formation, while others could strip material from the disk. Even minor interactions could influence star formation efficiency. The combined effect of mergers, inflow disruption, and halo heating would determine whether the Milky Way continues forming stars or begins a gradual decline similar to the Death Star galaxy. High-energy cosmic phenomena also play a role. Supernova feedback, stellar winds, and black hole activity can remove or heat gas in localized regions. Over time, these processes affect the galaxy's ability to sustain new stars. While individually small, their cumulative effect, combined with reduced inflows and halo heating, could slowly decrease star formation, showing that even massive active galaxies are vulnerable to long-term quenching. The Death Star galaxy provides a benchmark for these processes. Observations show that star formation can cease even when the galaxy retains structural integrity. This evidence suggests that under the right conditions, the Milky Way could experience similar processes, though its current gas supply and filament connections make this unlikely in the near future. Environmental changes, mergers, and internal heating remain the key factors that could lead to slow, long-term quenching. While rare, galaxies undergoing cosmic starvation are real. Comparing the Milky Way to the Death Star galaxy allows scientists to identify thresholds for star formation, gas depletion, and halo heating. Models suggest that a galaxy can remain massive and structurally intact while gradually losing the ability to form stars, highlighting the delicate balance between internal resources and external cosmic forces. Cosmic collisions remain one of the most significant speculative factors. Future mergers with Andromeda or other satellites could alter gas dynamics, redistribute star-forming material, and influence star formation rates. Environmental starvation, combined with tidal stripping, could gradually push the Milky Way toward quenching, though this would take billions of years. The rarity of this combination of events explains why Death Star-like galaxies are uncommon, but possible. Even small shifts in cosmic conditions matter. A slight reduction in filament inflows, minor satellite interactions, or temporary increases in halo heating could begin the process of slow quenching. Star formation would decline over time, with molecular clouds becoming less dense and fewer new clusters forming. While this process would take billions of years, it demonstrates that galaxies are not immune to environmental and internal forces. The Death Star galaxy proves that quenching is possible without dramatic events such as collisions or explosions. Isolation from inflows, halo heating, depletion of molecular gas, and outflows can slowly end star formation. Applying this knowledge to the Milky Way shows that, while unlikely in the near term, similar conditions could occur over cosmic timescales, potentially leading to a slow decline in star formation over billions of years. Multiple factors interact in complex ways. Gas inflows, halo heating, mergers, outflows, and internal high-energy processes all influence star formation. The Milky Way's current stability relies on balanced conditions across these factors. Small changes over billions of years, however, could tip the balance towards stopping star formation, demonstrating that even massive, well-connected galaxies are vulnerable to long-term environmental effects.